Okay, good morning, or whatever it is in your current time zone, everybody. Welcome to Learn Python through Data Processing in Pandas, presented by Daniel Chen. The session will be 4 hours. We'll have a few breaks in the middle and hopefully a long one, or a few breaks along the way and hopefully a long one in the middle. There's a chat tab here so you can discuss things there. There's a Q&A tab, and then there's also a Slack channel that should be obvious if you know how to navigate things in Slack, and if you don't, just ask in the chat and somebody else will help you, I'm sure. Okay, I think I'm just going to bow out of the way and let Daniel get started, so go ahead.
All right. Hello, everyone. This is, I guess, the second year that we're doing all of this remotely, but we've all learned a lot in the last year of running these workshops remotely, so hopefully it's much better today than it was a year ago. If you haven't already, I put into chat the GitHub repository or link to the GitHub page for today's workshop. If you know your way around Git, I'll let you do your own thing. If you do not know your way around Git and GitHub, to get everything down to your computer, there is this green code button here at the top. If you click it, you can download the zip file and you can save this somewhere onto your computer. So for me right now, just to make life a little bit simpler, I'll dump it onto my desktop. And just like any other zip file, do remember to unzip the folder. A lot of computers these days sort of like fool you into thinking that it's unzipped. So you do want to make sure that that folder is unzipped. And once you're there, you should have all of the data sets that we'll be using for today. And the other thing, hopefully, that you already have done is down here at the bottom, there were installation instructions for setting up Python. So if you use the Anaconda distribution, everything would already be set up for you. If you do not have the Anaconda distribution and you're essentially rolling your own Python installation, make sure that you have the Pandas, scikit-learn, and Seaborn libraries, and that's all we really need for today's class. As far as questions go, I'm sort of pretty used to doing the whole check across my screen, so use whatever is more comfortable for you. You can use Slack. There is a channel for Slack for this class. If having a separate application is not just too many screens for you, feel free to use the chat panel in the AirMeet, and I should be able to see it. I know that there's also a Q&A panel, so hopefully it'll sort of do a little alert when someone asks questions there, but I'll essentially just be rolling my eyes across all of the chat interfaces, and hopefully I get your question. Next thing, if you have used the Anaconda installation, the first thing that we want to do is load up Jupyter Lab. And the way we do that is give me 1 second. If you're on Linux or Mac, you should be able to open up a terminal application. If you're on Windows, you should see an application called Anaconda Prompt. It should look more like this. You should see that on the top. And all you need to do is in the little text box, type in Jupyter Lab. And it should open up the Jupyter Lab interface. And I will make the text a little bit bigger. Yeah, boom, boom. Okay, don't exactly know how to make fonts bigger on Windows. So I'll end up writing this. Right. So you should be able to run Jupyter Lab in the terminal, and it should open up this page. And since there isn't a way for me to quickly queue, give me the thumbs up emoji. There's no actual thumbs down, so that doesn't help either. But I guess give the laughing emoji if you are still stuck, and the thumbs up emoji for if you're sort of ready to go. I can run a poll. Boy, this is. But I don't think I saw anyone. At least hopefully I didn't miss it. Oh, someone has a laughing emoji. So just as a quick recap before we get started and get everything ready, I'll try to have all of the bits and pieces on the same screen. So here is the page to the GitHub repository. What you can do is click on the code button, go to download zip, and download and unzip the file. That will give us the little data folder, and that's pretty much everything that we'll be working with. Hopefully you've already installed the Anaconda distribution for Python. If not, if you scroll down to the bottom of that page, it has all of the links for you. Once you have the Anaconda page, you should have and I'll put this, on Windows, you should have a application called Anaconda Prompt. Open that, and it will give you a little terminal window and type in Jupyter Lab. If you are on Windows or Linux, simply open up the regular command prompt. On the Mac, if you use like Apple Space, you can type in terminal, or you can find it under applications, utilities, and then terminal there. And you can type in Jupyter Lab, and it should open up this window that you see on the right. Some of the questions was, what's the difference between Jupyter Notebook and Jupyter Lab? Essentially, there is no difference. We're going to open up a Jupyter Notebook, but Jupyter Lab gives you this like file browser on the left-hand panel. Some of the cool things, like you can preview CSV files and stuff like that, all in this interface. And you get to have multiple things open at the same time. So like you can, for example, open up one notebook and open up another notebook and have them like side by side. So it gives you this like tiling feature in there. So it's it should be a little bit more user friendly. Hopefully, I'm assuming because people said and mentioned that they wanted my font bigger, that my screen sharing is doing okay. With that, once we have Jupyter Lab open, since I dumped my stuff on the desktop, I am going to open up the desktop stuff. So I have my 2021-07 13, today's the 13th, whoa, SciPy Pandas folder. I'm going to open that on the left-hand side. And we can click the little plus button up here and click in new notebook, and you'll see that the untitled notebook should show up in the folder that we unzipped. If you don't have the Jupyter, I also realized that is Jupyter Lab not part of the Anaconda distribution? If it's not, you can, instead of Jupyter Lab, you can type in Jupyter space notebook. And that'll work totally fine. The main thing is when you are in the interface in either Jupyter Lab or in Jupyter Notebook, please make sure that you go to the folder first and then create a new notebook so it shows up in that folder, and you can confirm it on your actual computer. So if I go to my actual desktop, in here, you'll see that that untitled folder is actually in there. What ends up happening is if you open up Jupyter Lab or Jupyter Notebook, it starts at a default file location. And if you click Create Notebook there, it creates the notebook there, and then it gets really hard to find the data sets that we're going to be using in this project. Once you click the little plus, it should give you a launcher, and all you need to do is to create the notebook is to actually click the Python 3 notebook, and it will create it for you. And that should get us up and ready. There was one question that I missed. Let me just make sure. So one of the other questions was, can you make changes to your code in Lab just like in Notebook? Yes. So essentially, when we open up Jupyter Lab, so think of Jupyter Lab as this whole thing that's running in the browser. The individual notebook, when we click on Notebook, is the regular Jupyter Notebook. So think of Lab as like the next generation interface on working with notebooks. There's a bunch of caveats with that statement, but for this workshop, that's all you really need to know. If you want to use your own IDE, you can totally do that as well. For example, some of the people are mentioning using PyCharm. Totally fine. Just make sure that you're in the right project folder, and that'll just make it a little bit easier if you are going to follow along one, like exactly as I'm typing, just to make sure that you're in the right place so we can find our data sets. Cool. So let's get started. So this class is primarily trying to teach you Python, but from a data analysis perspective, and a little bit more about myself. So I am Daniel. I am currently a PhD student at Virginia Tech, and I actually study for my dissertation data science education in the biomedical sciences. And a lot of the stuff that I've learned trying to teach people in the medical domain really do apply to people everywhere when they are starting to program, or more specifically, when they're trying to use a programming language for their own data sets. And it's a little bit different from learning to program for programming. Like, I like to distinguish, there's a different type of ordering, mainly the ordering of the topics that you need to learn when you're trying to program in Python as a programming language, and program in Python for a data science or data analysis like field. So the main focus here is, I'm going to assume you already have a data set that you already want to do analysis on, and then that's our main starting point, versus trying to write all of the code, trying to pull down with APIs to get a data set or curate a data set ourselves. And we'll just start at the position of, hey, I already have a data set, and then how do we go from there? So that's sort of the starting point of where we're going to be, and that sort of changes, and that's how it differs from if some of you took the class from yesterday on the more general Python programming intro. There's going to be a difference in the ordering of the topics presented, but at the end of the day, you eventually will need to learn everything, but the order is a little bit different. Okay, so with that, I haven't seen any, what did I say, laughing faces. So I think I am good to go. So the first thing that we, hopefully that's just not a actual thing. Maybe I shouldn't use a laughing face as a as a way to go. So give me 1 second. Okay. All right. So the first thing that I want to do, since we have our launcher open and click on Python 3 to open up our new notebook. If you're using Jupyter Notebook, at the front page that you see on the top right corner, you should see like a drop down that says new. And if you click that, you can click on Python 3 and then it will open you into a screen that looks like this, what I have on the right hand side. I'm going to make my screen a little bit bigger. And the first thing I want to do is you can right click the little notebook, the text that says untitled Python notebook. You can hit rename, and I'm going to rename our first notebook called 01-intro. One of the things that I highly recommend is if you are running multiple scripts and you know that this code needs to be executed in a certain order, or you're working through stuff in a certain order, begin your files with a number just so they sort in proper order and you're not relying on the alphabetical sorting. That will save you a lot of confusion moving forward. And our first little command that we'll run. So we are going to be learning a library in Python called Pandas. Pandas allows us to load tabular data sets, like an Excel file or a CSV file, into Python, and gives us that tabular data that we can work on in Python. So the first command that we're going to do is we need to load up our Pandas library, because it doesn't automatically happen when we are just start up Python for the first time. So the way we do that is we type in import pandas. And if we hit Shift Enter, it'll run the code and give us a new code on the bottom. If you hit Control Enter, it'll simply run that little block of code. Or if you have your cursor in the little text box, you can hit the little play button and it'll run that code and give you another box on the bottom. So there's multiple ways you can execute your code in Python. The first thing that I want to show you, and just for the recording itself, we can say pandas dot dash dash version. And this is how you check VRSION, if I type it correctly. I am currently, at least on this computer, running 1.2.4. The main thing is hopefully you're running a version that is 0.24 or later. That'll make a little bit more sense in the next hour. But this is just the Pandas version that I'm running. You might see different errors or warnings. The code might be a little bit different, but it shouldn't be that shouldn't be the case for today's workshop. But if you ever end up needing help, this is a good first place to sort of check. All right, so we have pandas loaded. And the first thing that we want to do is use one of the functions in pandas to load up a data set. So how do we do that? So if we think of pandas as this whole library, and it's got a whole bunch of things that we can call or use within it, there is this function called read_CSV. How do we actually access that function within Pandas? Well, we first have to say Pandas, because think of it as like the book or the library that we're using. So we're first using the Pandas library. We use the dot in Python to sort of access something inside of the Pandas library. And the dot comes into play all over the place in Python. So we're using the Pandas library. We're using the dot to access something. And then in Pandas, there's a function called read CSV. And we call the function using a set of round brackets. In this set of round brackets, you can use single or double quotes. I'm going to be using double quotes here. And in here, we point to the data set that we're going to be using. So sort of the nice thing about using Jupyter Lab is I can sort of show you the file panel at the same time as I'm going. So you notice that here I have my intro notebook that I renamed from the beginning. And there's this data folder that we want to go into. And the first data set that we're going to load is this gapminder.tsv. All right. So what I need to do is first point to the data folder and then the gapminder data set that we want to use. So how do we do that? In the set of double quotes, we can say data. We can hit the slash button. So that is the slash that is towards the bottom right corner on a US keyboard. And then we can say gapminder.tsv, and you can hit the tab key and it will sort of try to autofill as much as it can so you don't end up with a typo. If we try to run this block of code, so Control Enter or Shift Enter, it's going to give us an error. If we go back to the beginning, it's going to say a whole bunch of weird things. And that's mainly because we are using the comma separated value function to read in a tab separated value data set. And so how do we modify or change the function call? If we hit a comma within the round brackets, there is another parameter or another way we can change this function, change the function's behavior, called sep for separator or the delimiter. And in here, in single or double quotes, we can put in \t. So this backslash is a different slash from that. And here, this is how computers interpret the tab character. So we're really saying, use this data set that I'm providing you in this location, read it in using tabs instead of the default comma. And then you'll see here, what you should get is a nice prettier output of the data set that we will be working with. So with that, give me a thumbs up if you were able to load up this data set. All right, and I guess use the I want to avoid using laughing because I realize like that's just like super trolly when I stare at it. So use the celebrate if you're having like massive issues, and hopefully one of the people can kind of help you in the background. So let me copy and paste this little block of code into the text here, and I'll also put it into Slack. So that is a little block of code that we ended up. So that's a little block of code that we are using. If tab autocomplete is not working, it's a little weird. Sometimes it's kind of glitchy on my end as well. So hopefully it gets a little bit better. Sometimes like tab autocomplete just works for me later on. I don't exactly know. Does Jupyter Lab autosave? I believe it does keep a like checkpoint file. So there is like an autosave feature, but you should get into the habit of actually saving this notebook. regularly, but yeah, there is an autosave checkpointing feature. So if you accidentally do close everything and load it up, it should load it up for you in your last state. For those of you who are having loading issues, the most important thing to keep in mind is the notebook file that you have should be in the same folder as the SciPy Pandas folder that we got from the internet. And the easiest way to check is you can confirm it not in Jupyter Lab or Jupyter Notebook, like confirm it in your actual double clicking browser view. If you navigate to that folder, so for me, I know I put it on my desktop, the notebook file and the data folder are all in the same location. If it's not, mainly if the notebook file that you're creating is not there, then that is going to be an issue with finding the data set. So finding the data set is going to be a separate issue from like the actual version of Jupyter Lab. So those two files, or that file and the folder, really need to be in the same place, because otherwise it's not going to be able to, you're not going to be able to say data/Gapminder, because it's going to be like, oh, I'm starting from a different starting location and there's no data folder there. So if you end up, for example, if I mistype this, if you end up with a file not found error, that's probably because one of those things is not in sync. You either typed it wrong, the notebook's in the wrong folder, or or something else with you're in a different location, or Python thinks you're in a different location than what you think you're in. If you want to rename the folder, you can right-click the actual name on the top and click on Rename Notebook. That's how you would do it in Jupyter Lab. In Jupyter Notebook, you should see the name on the top, and if you simply left-click it, it should open up as a text field, and you can left-click to open that. All right, so the next thing, this will be another review through the process, but you'll see a lot this particular line that says import pandas as PD. You'll also see a lot of people, not really people who use pandas, but you might see another way of importing things that looks like from pandas import star. Don't do this. So these are two other ways you can import or get in all of the functions within a library. In the previous example, you notice I wrote pandas.read_CSV, but if we use this top notation here, instead of saying pandas dot every single time, we can now simply say pd.read_CSV. And I can show it to you. I can literally copy that previous line, paste it, and instead of pandas.read_CSV, I replace it with pd.csv. It is going to be exactly the same code, and this PD is serving as a shortcut or an alias, and it really just is a way to save typing because some of the Python libraries are pretty long, and so you don't have to type in all of that. You don't want to use this notation that I have commented out because it'll load everything all in one go, and you don't have to specify that beginning of where it's coming from. It might sound like a good idea at first, but you end up in a scenario for, let's say you write your own mean function. NumPy, other libraries have their own mean function, including base Python. So when you call the mean function, how do you know which mean function it is? Typically, it's the one that's the last one that got loaded overwrites everything else. And so that just gets really confusing. And so one of the good things in Python is you have this feature to be really explicit, or you have to be really explicit. I also program in R, and this part is sort of like more or less optional, and it's kind of weird, especially if you've been programming in other languages. So I'm going to copy this line of code. So that's the pd.read_CSV and send it to you guys. And so now we have loaded up this data set. It's not really useful if we just have, every time we want to do something, we load it up again. So let's save this to a variable. So I'm going to get out of the habit of calling it df for data frame, and I'll call it dat for data. So I'm going to say dat is equal to pd.readcsv. And now that you'll notice that it doesn't show up at the bottom, like it doesn't automatically load up anymore. And that's because now if I say dat, it'll load up my data set. So instead of reloading for every single operation we want, we can now work with this data set by calling on dat. Okay. So the first thing, if you load up your data set, or if you're working in Python in general and you get confused as to what you're working with, there's a built-in called type. And if you run that, it will tell you what this thing is. And this is important because this is sort of how you help yourself look for help. So if you ever get confused after loading a data set and you're like, what is this object? You'll see that this is a Pandas data frame object. And so if you need to Google for help, you can now say like, okay, I'm looking for Pandas data frame help and not Pandas other stuff or just a regular Python list or whatever. So this comes in given to you from Python. It's not Pandas specific. But it is a really good way to help you figure out what object you're working with. So the next thing you want to do after you load in your data set is to make sure that you have the correct number of rows and columns, or get a sense of how many rows and columns if you've never opened it before. So if we take our data set, so DAT, remember how we said pandas.read_CSV? That dot allows us to access different things within the library. Now this dot can also be used to access different things with our data set. So we have our variable DAT, and it's got a different like attributes associated with it. One of those attributes is called shape. So shape gives us the number of rows and columns in our data set. And this is something good, especially if you're coming from, if you're trying to load up sensor data, because typically those have fixed number of rows and columns. You can check to make sure that it was loaded properly. Mainly the thing that you would want to check to see if that sensor data set had column, that first row being column names, that it was read in properly, or if it's sensor data that doesn't have column names and it's really just a matrix of values, you don't accidentally read that first row as a column name and you're reading it all as data. And so that's one thing that you want to check. Another feature of data, of our data set, is there's this method, or a method is a function that an object can call. So type is a function and you give type something to do, like an input. Shape is an attribute, like, hey, it's sort of like, hey, I'm Daniel, what is your name? And name is an attribute. There's another way you can call like functions, and they're called methods. And those are things that objects can do on their own. Like you can say, hey, Daniel, you yourself run the walk forward command, right? And so the data frame object has a method called info, and you can distinguish between attributes and methods by attributes do not have round brackets after them, and methods do. And so we can say df.info, and it will tell us a bunch of information about itself. So you can see that how many rows it has, how many columns it has. So it starts from 0 to 5, the name of the column, how many non-missing data sets or non-missing values in here, and the actual type. So you can see that some of the data is integer, some of them are floating point. If you see something called object, it probably means string, like regular text characters or some generic, anything that's like not a number essentially will probably show up as an object type. There's another type specifically called category, but unless you do other things, it doesn't automatically show up like that. So one of the questions I was getting is like, why DAT instead of DF? It's sort of like a bad habit. Like it's DF for data frame, but DF also in a lot of other libraries and packages ends up being like the density function. At least that's what it is in R. So you kind of want to, if you can avoid it, don't use variable names that yourself are using that are like variable names or functions of other libraries. And so that's sort of a habit I'm trying to break out of myself. If you're getting a file not found error from loading the dataset, again, make sure that the notebook that you're using is sibling with the data folder. And that way you can say, go into the data folder and then the gapminder TSV. The way, if you're also still having problems, if you run pwd, so this stands for print working directory, and this works in Windows as well, and this is a benefit of using Jupyter notebooks, it will tell you where your starting point is. So if your pwd is not where you think you are, and you're getting a file not found error, that's sort of the discrepancy. That's how you can figure out what's going on. So another question that I was getting was like, what is the object D type? So the D type or the data type that is called object is the most general thing. So another, since your question also talks about other programming languages, like just like in object-oriented programming, you have like an object, which is like a thing. And so this is just saying that, hey, this is a column of things. So it's super generic way of specifying the column type. And that's part of it is also because in Pandas, if you also think about how your spreadsheets are stored, in any given row, you can have mixed data types, but in any particular column, all of the data types need to be the same. And so having object is really just saying, hey, this is the most generic thing that we can put in here. Typically, it means it's a string. But it's just another way of saying like something super generic. And you can confirm it if you look at your data set. You'll see that, like, for example, country is of type object, and you see it spelled out, like here it says spelled out Afghanistan. Then you can confirm to yourself that, like, oh yeah, this thing is a string. All right, so we talked about attributes and methods. What happens if you say dat.shape and you forget it's an attribute and you run it as a method? Then you'll get an error. In this case, it's saying tuple object is not callable. What is a tuple or tuple? So a tuple, if we remember what shape looks like, is this. This is the output. And it's a tuple. Think of it as a list of things. It's technically a list that you cannot change. And it's because we put in round brackets, it's saying like, hey, see this list or this tuple? I want you to run it as a function. And that's why it's giving you this error message. It takes time to figure out which things are methods and which things are attributes. That's, you know, the story I tell myself is sort of like, hey, shape is an attribute because it's a thing, but info is something it has to go and calculate. So that's why it's a method. So different things will behave differently. It's sort of over time that you get used to calling and remembering which are attributes and which are methods. All right, so another method that we'll cover, and this is really useful for things when you load up your data set, is the head method. This will give us the first 5 rows of our data set. And then we have tail, which will give us the last 5 rows of our data set. Again, these are really useful when you are trying to just make sure that your data set was loaded correctly. Another thing that you'll see me do instead of running head and tail is I'll run dat.sample, and with this sample like 10, and it will give me 10 randomly selected rows in my data set. And this, again, is something that you can do to sort of spot check, like, do things make sense? And what generally is going on in my data set. And so head, tail, and sample are really useful for checking and spot checking like your contents. So we have our data set, it's loaded. There's three major components to every Pandas data frame object. And we can access those components one at a time, right? So if I look at the sample, you'll notice that at the top here, we have our column names. Down here, we have like the body, like the actual data set values. And then the thing that looks like the row name, we also have access to that as well. And those things have different attributes to access them. So if we say dat.columns, we can get the results of all of just the columns of our data set, right? And the question was like, what is the object data set data type? So this is just saying that like, hey, your column names are all individual strings. And why would you want to be able to do this? Especially if you load up a data set from Excel, you want to eventually check the columns because sometimes people like put spaces in their Excel column names to like align them properly in their Excel spreadsheet. And so you can imagine like year is different from year space or space year, right? And that's going to cause a bunch of headache when you start programming with your data. So looking at the columns is another, and looking at how things are quoted in here is a way to confirm what is the actual spelling of these columns. The row names themselves, sorry, you can see this is my habit. The row names themselves is called the index. So this black bolded text here that doesn't have a column name is called the index. And instead of saying by default like 1 to 1000, 0 to 1703, it's just going to say the row names are starting from 0, ending at 1704, incrementing by 1, and not including this last piece. And that's how the row names are being calculated. Yeah, it's called the index because the row is too obscure. It's also called the index because you can have multi-level indices, very similar to how you can have multiple levels, grouping levels. So Pandas, a little bit more of the history. Panda was created by Wes McKinley when he was in a, oh gosh, I'm forgetting the words. The words are hard for me this morning. It was created by Wes McKinley when he was essentially working with a bunch of stock data. And so you can have an index that is like the ticket, ticketer, and the year. And you can much more efficiently slice out or take out different parts of your data set. And so that's why it's called the index. But yeah, it would have been nice if it was just called rows to make it like, more consistent with columns, but so you can have multi-level indices, you can have multi-level columns. That is way out of scope for today's workshop, but you can do that type of work. The last component, dat.values. The values part is the actual body of our data set, and you can access that as well. What's nice about this is you'll notice it comes in as an array. And if you've seen or attended some of the other workshops at SciPy, and you'll see it in the talks as well, when people are talking about NumPy arrays, this is the NumPy array representation of our Pandas data frame object. So one of the question was about why does it stop at 1704 when the row number actually is at 1703? So since this is me also trying to teach you a little bit about Python as well. So Python runs on what is known as left inclusive, right exclusive. Let me, boom, boom. Please don't make me. Okay. Get out of this. All right. So Python is known as left inclusive, right exclusive. So in general, super sensitive, but I'll deal with it. So if I have a couple of people and they are separated by fence posts, and these fence posts are labeled 0, 1, 2, and 3. The way I get person number 1 is I say start from 0, end at 1, and I get 1. If I want to get, all of these rows, all of these people, I will say go from 0, end at 3 to get 3 people. So that is the left inclusive, right exclusive nature of Python. And that's why it's showing up as like you stop at 1704, even though the last person, so this is person number 0, person number 1, person number 2. That's why it seems like one more. And it's because it's counting that last fence post to gather everything in between. So that's essentially how Python is doing its numbering. And yeah, the artistic skills is even worse because I realized my tablet is like transitioning across all 3 of my monitors, and usually it's only working across 1, so it's like super sensitive for the pixel density of the tablet. But that's how that works. So yeah, it is including the left endpoint, but not including the right endpoint. Yeah, so it's like less than, equal, greater than, only. Yeah, something like that. It's really greater than, equal, and less than only, I guess, if you want to think of it that way. All right, so we have our data set. We have a way to access all of those components. What are other things that we want when we load up our data set? So there's going to be a time where, let's say, especially so I work with healthcare data sets. Sometimes I only care about a few of the columns in our data set. It's not part of the research study. So this will happen in like GWAS studies, GWAS, GWAS. I don't remember what the acronym stands for. It's like genome-wide something. And I only care about a couple of those SNPs, really. Or maybe you are on Kaggle and you download a Kaggle data set and you don't care about the ID column of your individual because the ID shouldn't play a role in your outcome. So you want to be able to select different columns from your data set. So we can do that. The way we do that is we can say our data set, so DAT. We can use square brackets. So in Python, square brackets has a couple of meanings. One of the meanings that square brackets do is take something out of a container, right? So our data frame is a data frame of rows and columns, like there's data stored in rows and columns. If we say, hey, I want you to take out something from my data frame, it will pull something out by its column. That usually makes sense because usually we care about the thing that's all the same data type and not by rows. And I'll show you how we can select things out by rows in about 10 minutes. So the first thing that we will do is pull things out by its column. So we can say, hey, just give me the country column, and it will give you back your data set from just country. You'll notice that it printed out a little bit differently. And this is one of those things that are, it behaves a little bit differently because we're only pulling out one thing, right? So if we go back to our data set before, you can see like it's got this nice little pretty printout of of our data frame. But when we pulled out a single column, it was less pretty. And that's because if we go and look at the type of this, you'll notice that it's no longer a data frame object. It is known as a series object. And that's important because one way you can think of how those two things are related is a data frame, like I said, is a whole bunch of columns that is all stuck together to form one tabular object. Each one of those columns has to have the same data type. And that's why when we ran info, it told us the D type and why some of it said object, because it's all strings. Because each column has to have the same data type, each column can be thought of as a single object, and that object is called a series. So a data frame object is composed of series where each of those series is a column of our data. And then for those of you who work in the NumPy world a lot, a series is an extension of the regular NumPy object. And so that's how all of these libraries in the SciPy ecosystem sort of relate to one another. It's really essentially almost all built on NumPy arrays and some extension of it. So let's say we want to, and I can totally save this to a variable as well. So I can say country is equal to dat of country. And now I have a data set that's just country. That's great. So I might sometimes save these to a variable, sometimes I won't, but just know you have that option available to you depending on what you need. So selecting one column is useful, maybe not. More typically, you're going to be selecting multiple columns, so we can do the same thing as well. It's still DAT square bracket because we are going to be pulling something out of our data frame object. But now that I want to select multiple things, the square brackets are also the Python way of creating a list. Right, so that's why you'll see this weird double square bracket notation. It's because the outer one tells Python, hey, I'm going to pull something out. And the inner one is saying, I'm going to give you multiple values. And so if we want to pull out country and pop, we can pull out, here's multiple values, country and pop. And I want you to use that to take something out of our data frame. So the question that I was getting was creating country variable is pointing to the original data, not making a copy. That is correct. It is not making a copy. There is a way, I think you can literally say copy. Yeah, you can actually say copy and it'll make a proper copy. But yeah, it is passing by reference under the hood. So be very careful. Sometimes when you start modifying things in Python, it will warn you if you are making modifications that it can't know of. But just keep that in mind. The other question is, how do you possibly keep track of that? So this is a behavior that is essentially Python wide. So it's not just specific to pandas. So in some sense, you don't really need to keep track of it because it's essentially how it works by default. And typically, and the reason why it's doing it this way is also it saves a lot of memory because most of the time we just want a subset and keep working on that subset. And we don't want to make a full copy of that every single step. So that's sort of what's going on there. And one other thing, so if you do end up programming like building libraries or functions and things. So I'm going to use the country data set, country column again. You notice that originally when we just pulled in country, it gave us the series object. It's also okay to have an object or a list that is one value. And that will give you the country as a proper data frame object. That's one column instead of a series that is like a vector of values. Something that might be useful, I find that this is more useful if you are writing libraries and functions, because now you are always guaranteed a data frame object and you don't have to account for, is this a series or is this a data frame, et cetera, et cetera. So that's sort of a trick if you end up, building your own libraries and stuff. How do I show the two side by side? I think this works in, nope. I don't have the plugin installed. Shoot. Hold on, let me just run it. And that should work. So one gives us the vector value and the other gives us like the actual column value. So that's sort of the visual distinction, and also it behaves differently. So if you get the type of this, it's a series, and you get the type of this, it's going to be a data frame. So something to keep in mind. So the series, think of it as like a series is a NumPy array, which is like a really fancy list. So think of this as like a list of values that's like Afghanistan, all the different countries in our data set. The data frame is a actual column, like rectangular data set that we loaded in. It just so happens to have one column. So vector and series, I sort of use interchangeably. Vector comes from more of like the mathematics and R world, and series is the formal object name that you'll hear being used in pandas. So those all will mean the same things. Think of it as, and I'm trying to distinguish it from like, here is a proper rectangular data set and I'm pulling out a column of values. So there is that slight distinction. For the most part, it probably won't matter. A lot of functions you use will handle series and single column data frames, but they might not. And so you have to be a little bit careful of how you specify your columns. All right, so we talked about how to get multiple columns out of our data set. Let's talk about how we can pull out rows, and then we'll take our first short break, and then hopefully if anyone's having other like random installation issues, we can deal with that as well. So how do we look at rows in our data set? I'll look at sample of, sorry, it's DAT because I'm still in that habit. So here's a random sample of 10 values in our data set. Maybe I want to only pick out a couple of them, right? So value 779, row index number 779 for Italy. Maybe I want to pull that one out, or maybe I want to pull out the first one, which is, remember, Python counts from 0. So instead of using the square bracket notation in Python to pull out columns, we use the LOC, essentially like the attribute. It's really called an accessor, like we access things from our data set. And in here, we can say, give me the value that is 0, or essentially the first one. What did I say for Italy? It was 779. So we can also say, give me the value, give me that row of value, that's 779, and it'll give us Italy. And you'll notice that it's giving this back to us as a series object. How do we know it's a series? Well, we can run type over it, but also if we're in the IPython Jupyter notebook system, it doesn't look pretty, right? It's not as pretty as this. And that's part of it is because we're passing in one value. So we can do multiple values just like before. We pass in a list object with square brackets. So I can say, give me the one that is named 0 and 779, and we got Afghanistan and Italy. And that's useful, more useful calling things this way if you are working with sensor data. If you know a little bit about Python, you'll notice you will know that using negative numbers will count from the back, right? So we can say like, given, apples, bananas, cherry, given that list, the -1 object is cherry because it's the last one, and negative values count backwards. Not necessarily the case here, because if we gave -1, like give me the last value in here, we get a value error. And that's because LOC, or location, is doing essentially like a text matching of the index, right? We don't have the actual text for the index called -1. Maybe in some data sets you do, in this particular data set it doesn't, right? And so that's why we get an error when we try to run, oh, give me the last row, because there isn't a like actually literally -1 for the index value. So how do we so that seems problematic because sometimes you want to specify by the absolute position, not necessarily by what's labeled, right? So let's say, for example, I scramble my data set. There's a difference between the value that contains 0 and then the absolute position of 0, which is the first row, right? So those two are a little bit different. They'll come into play. We won't really talk about this, but when you start combining data sets, that's when it will come into play. So how do we get around specifying the absolute position versus the actual name? So instead of LOC, there is one called ILOC for index position. And then we are able to pull out the last object. So that's something that you might use if you want to just check the first and last row. You can either use head and tail, or you can use iloc iloc and then a list 0, -1, and you'll get the first and last row. Right? There's many different ways you can deal with that, but there is a difference between LOC and ILOC, and hopefully that sort of showed you the difference there. Not really an issue anymore, but there used to be one called IX. I should almost just stop teaching this. They got rid of it in the newer versions of Python. You might still see this in some certain Stack Overflow solutions, but IX essentially behaves like LOC until it doesn't. If it can't find that value, then it will behave as ILOC. And you can see why that gets really confusing and super problematic, because it can behave like two things silently. And they just eventually got rid of it. So the other question I was getting was, please share the notebook. Yes, one of the things I will do during the first break is send this notebook up to the GitHub repo. I will do that during every break so people can catch up and look at my notes. And also, throughout the rest of the conference, if people ask me questions, I'll use that repo for more additional links as well. The last thing I want to show you is how we can subset both rows and columns. Whoops. So how do we get both rows and columns, right? Sometimes we want to select like only the country and the population, but give me certain rows, right? So that's where we can keep building on that LOC or ILOC notation. This notation actually has two parts to it. There's a comma that distinguishes both parts. The thing to the left distinguishes how you want to subset your rows, and the thing to the right allows you to specify how you want to subset your columns. It's very similar to how mathematical matrix notation is written. So we could say, and in Python and general lists, if we use the colon, it's simply saying like, hey, start from the beginning, colon, go to the end, right? So we can say like, give me my entire data set. That's one way you can specify your entire data set. I'm showing this as an example that we can build on. So think to the left, how we subset rows, think to the right, how we subset columns. So we can actually say, think to the right, pass in multiple values, for example, year and pop. And just like how we were using square bracket notations on its own, we can use this type of notation to just get certain columns back. This is kind of weird, but the benefit of this type of notation of selecting both is now I can put in a list object for the rows. And so, for example, if I want the 0th index, 10th index, and 100th index, we can select our rows along with our columns. And this row notation doesn't just have to be the actual numbers, right? They can be a vector or a list of Boolean values, like true false values. And so how do we get true false values? So let's say I take df country, and let's say I only care about the values where it's Zimbabwe. And I'm using this because, sorry, it's DAT. I'm using this because Zimbabwe is the last country here. And you can see I get a bunch of true false values if the value of country is equal to Zimbabwe, right? And I get this vector or this series of true false values. Well, I can plug in this series of true false values into how I'm selecting my data set. So if I say dat.loc, and by default, it'll only work on the rows first, so I don't have to specify the column notation, but you can, if you can write it this way. I will get, and the way I pronounce it is, I'm looking at my data, I'm going to be selecting on things. There is the selection. The thing to the left is how I'm going to be selecting on rows. So how am I going to select on rows? I'm going to select the rows where the country, the value of country is equal to Zimbabwe. That's how I'm selecting on rows. And then I'm pulling in all of the columns. And now I have a data set of all of my, of just Zimbabwe. And I can pull out separate data sets, separate columns if I need. What if I only care about the values that are listed in like the life expectancy of Zimbabwe, but only after 1990? So now how do we build on this set of Boolean conditions? So here's sort of when the notation gets a little wonky. Part of it is because of how Pandas is built on NumPy arrays and how that's all optimized. In regular Python, you can say and, like AND or OR to say and, or use the and or operators. Not so much when you're working in like essentially the high performance computing world. You have to use the ampersand or pipe operator. So I'll put this as a comment for and the pipe for or. So let's say I want the country where the value is in Zimbabwe and where the year is greater than 1990. Two different things about this notation. Those two components have to be in round brackets, and we have to use the bitwise operator. So these are known as bitwise operators. I'll write that in. And so that's how we can select on multiple things. So it is a little bit past top of the hour. Let's take a short break, come back at 15. So it's about 5 minutes. I will push this notebook up to GitHub so everyone has it. If you have any questions, put them in Q&A or in chat, and then I'll answer them when we come back. So I won't answer the questions unless it's like an installation issue. So we'll come back at 15 past the hour.
Hey, Daniel, can you take a look at Pranav's question? Because I tried that and I get the same result as they do, but there's some weird syntactical thing that I'm just not seeing.
Yeah, hold on. So I think this is what was copied. Or not.
Yes.
I'm pretty sure I just copied that.
Right.
But I'm not getting that error message, right?
Well, it's not an error. It's just, so they're right. I mean, it ignores. Oh, wait, hold on. What was your original thing?
Oh, I see. It's ignoring the. Hold on. Did mine ignore it as well? No. Okay, mine did. Mine did what it was supposed to do. Okay.
Oh, 1900 versus 1990.
Oh, okay. Yeah. Okay. I almost lost my mind too. I was like, what? But yeah, so 1990, not 1900.
And by the way, for people who are not programmers, that is the kind of thing you could stare at for literally like hours and hours and not figure it out, and somebody else could walk up and just point to it and say, oh, it's 1990 versus 1900, and you would never have noticed that. Don't feel bad.
Yeah, that the typos are the lessons that you grow to search for those first. And you still miss. Okay, so we're back at 15 to the hour. So just as a quick recap of what I ended up doing, if you go back to the GitHub repo right now, and I'll repaste it for those who are came in late. If you click on 01 intro, whatever I just did before break is now up there, so you can use this as your reference forever. And the installation instructions are down here if you scroll down a little bit. And most of my notebooks, except for the one I'm going, every new notebook I create is going to be totally separate from a previous notebook. So if you end up falling behind one of the sections, don't worry. The next notebook I create will not build on this one. So there'll be separate topics. Except for this case, because I'm going to keep building on this notebook for the last example. And then we'll switch over to a new notebook. So we are able right now to look at different views of our data, our different rows and columns. Let's go and ask our first question to our data set. One of the questions, because this is Gapminder data, so this comes from Gapminder, so it has for each country and year the average life expectancy, total population, the GDP per capita for that particular set of country and continent and year. So one question would be, how does the global life expectancy change over each year? So one way you can do this is, well, find out each unique value of year. So let's say pull out the values where year is 1952, then take the life expectancy column and calculate the average. And then do the same thing for 1953, if that even exists, or 54, et cetera, et cetera, et cetera. You can see that gets super tedious very quickly. And so one of the nice things is if you ever, and we're going to talk about how data should be structured, if you have a column of data that is like, I want a separate calculation for each unique value of this column, this is where we can use the group by feature. This feature exists in Excel. I think it's also called, you click like the data button and then you can do a group by operation. And the way group by works is this notion of split, apply, and combine. And I know that there's a Dask tutorial like right after mine, and you can come back and listen to it. And essentially, Dask runs on split, apply, combine. What does that mean? So we first specify the column we want to split our data set into. So we don't have to do that Boolean filtering for each year. We can just say, I'm going to give you year, And any calculation or function that you perform, I want you to run that calculation for each unique value of year. So do that splitting part for us. The next thing that we want to do is, okay, treat this as a regular data frame. If we look at type, it's not really a regular data frame. It is a group by, a data frame group by, but we can pretend it's a data frame object. So let's say I want to pull out just the life expectancy column. How do we do that? We can use our simple way of doing it, which is life exp to pull out the column like I just showed you. And for these columns, because they're built on a series object and because series objects are built on NumPy arrays have built-in some of the standard statistics methods built in for us. So we can say, calculate the mean. So that is the applying the mean function on each split of year, right? Split, apply, and then the combined part is once you've run that calculation, stick it all together and combine it and give me one set of results instead of however many sets of results. And that's super useful, especially when you have very large data sets. It's a great way to get very quick summaries of your data set as well. So this split, apply, combine is what group by gives us. Let's say we don't want to use the mean function that's part of the series object. We want to use some function from another library. We can do that as well. So we can say import numpy as np, right? So let's say we want to use the actual, be really explicit and use the numpy, the mean function from numpy. So let me copy this in there. So for the person that wrote this, only this part, you're missing that part right here, which is like run the actual calculation, right? So right now, if you forget this mean part, it's going to be like, yeah, here, I gave you this thing. And it's because no actual mathematical calculation or nothing was calculated yet. All it knows is I'm going to split everything by year and pull out the life expectancy column. Cool. Here it is. So nothing got calculated until you run that calculation. So let's say instead of .mean, we want to use the NumPy version of mean. How do we do that? We pass in AGG, or I think you can type it out as aggregate. Yeah, you can type in aggregate as the full word or AGG for the shorthand. And so what does that mean? Why is it called that? So you can think of certain functions. You can think of certain functions like mean. Mean is a function that takes in a bunch of numbers and gives you back one number, right? So I can take like 1, 3, 5, and the mean of that is 3. Contrast that with, taking the z-score or something. The z-score takes in a bunch of numbers and gives you back the same number of values. That is called a transformation function. That is that's why we're using AGG, because we're using functions that return one value and not transform. I think it's called .transform. We're not using a transformation function. So in here in AGG, we can specify np.mean to say, hey, use the mean function. We're not calling the mean function, not giving it values. We're just saying use the mean function on that thing. And you can replace that with standard deviation or whatever you want. So the question was, why round brackets and then square brackets? So this is where the notation and building up and running type becomes really useful when you're trying to break down the components. So let's say I write in type here. Right here, it's saying, here's a data frame object, right? So I'm just using group by as a method, passing in year, it's giving me a data frame object. Pretend this is a regular data frame object, just like before at the very top when I first showed you how to subset columns right here. given a data frame, how do you pull a column? You're using square brackets. And so that's why our notation down here is then pulling the column, and we're getting a series object back. Given a series object, we can perform certain mathematical built-in calculations, and that's why the code ends up looking like that. And so if you ever get confused, that's why I always suggest running the type function. If you ever get confused with different portions. So what is the actual results here? What does it mean? It means in our entire data set, the average, because we used mean, life expectancy, because that's the column we pulled out, in 1952 was 49 years. And then it also gave us the average life expectancy in 1957, 1962, et cetera, up until 2007. And so this allows us to run this very quick calculation without having to subset, I don't know, like 15 times. The other question is, why use AGG NP.mean instead of just mean? This notation here allows us to put in any function that we want. So Pandas comes with mean, standard deviation, and some other stuff. But let's say you have your own calculation, like maybe you want to calculate, instead of arithmetic mean, you want to calculate geometric mean. It's a slightly different formula. You can either write that formula, that function yourself, or pull it from NumPy, and then you can put that in there instead of using this version of mean. So in our case right now, doesn't really matter. It gave us the same results, but this is how you sort of expand it to the next if you need something more specific. The last thing I want to show you is all of these components here. We could pass it in as a list. So let's say we want to break it down by year and continent, and we want to not only look at life expectancy, but we also wanted to look at GDP per cap and population, if I put in my quotes correctly. And here, you'll see that for each year and continent, I get separate means for life expectancy, GDP per cap, and population. If we want, we can keep going. In here, we can put in a list of different functions. So instead of just mean, we can put in np.std for standard deviation. And now we can get a bunch of breakdowns by a bunch of different things. And the only thing that's changing is instead of a single value, we're putting in a list of values. When your code ends up being super gnarly like this, what the Python community has done, hold on. They have navigated to this notation where they put the whole thing in round brackets. So put a beginning round bracket and an end round bracket. And before each period, they put, or before each new thought, they put a new line. And you can do that because a little round bracket treats it all as one piece of code, and you get the same thing. And the benefit of this, and this is why people call it dot notation, is you can say, oh, what did I do? I took the data, I did some group by operation, selecting some columns, and then I'm running an aggregation function. So it makes it much easier if you just look at the first word down each line than trying to parse out across. And your results are going to be exactly the same. One other thing, because this ends up being super useful, let's say you want to save this as a data set. One of the things that ends up being weird is you'll notice hey, 2007 and all of these columns, it's printing out weird, right? And if we look at the columns, it's printing out weird. I talked about using the visual printout as a reference, or use it as essentially a smell of something's different. We talked a little bit about multi-level indices. This is a multi-level index, and it prints out like this. So we have a hierarchical structure for columns and rows. Out of scope for this for this workshop, I personally also don't use them as much. So how do we flatten this data set? Because we want to save it out and work with a regular data frame, not just this like weird indexed data frame. So the way we can deal with that is at the end of all of this, all we need to do is type reset underscore index, and then we get a nice flat data frame back. I have to go figure out like how to do it for the columns, but you'll see here that the rows are now flat. And so now we can work with a regular data frame, because otherwise the LOC and ILOC would not have worked. It's because there's two levels in here that we have to specify. So using reset index, I have to figure out, I don't remember off the top of my head right now, how to deal with the column hierarchy. But the rows are usually the most important. And now you can save this out to an Excel file, CSV file, next person in a pipeline, et cetera, or your next part of the analysis. And all you have to worry about is, hey, this is a regular data frame, not some multi-index data frame, because those behaviors are different. Okay, cool. So let's create a new notebook. The intro notebook is over. I saved that. And let me put that up on GitHub right now. Git commit. Okay, so that should be, this notebook here should be on that GitHub page. If you want to look at that stuff for the code examples, you can, but I am going to move on to the next topic. The next topic we're going to talk about is thinking about how to structure our data sets. Again, I'm coming from the world of like, we are given a data set, or maybe we're curating a data set, like in Excel. So sometimes there are different modes of, it's easier for me as a human to enter data this way, but then the computer needs data in another format. How do we go about dealing with that? So if we Google tidy data, the third paper here is Hadley Wickham's tidy data paper. Hadley Wickham is the chief data scientist at our studio, and he wrote this paper back in, I believe this is 2014 is when it was published. And it's a very good paper. It's R focused only towards the bottom. So you really only need to read until section 4. Everything else is very applicable to general data processing. And we'll talk about this paper. Essentially, rows and columns are a little bit vague in terms of what they mean, right? So in this paper, and we're essentially doing a small journal club on this paper, rows and columns represent different things. They're a little bit ambiguous. You can see here, given a person and treatment values, all I need to do is transpose them. Same bits of information are being stored, but they look different on our paper. And so that means that like we don't really have a good way of describing what is a row and what's a column. There's benefits for both of these. Let's say you're manually curating this data set. Maybe it's easier for you to say, for each person, enter their treatment value this way. Or maybe you have treatment A, treatment B, and you're going to enter each person column-wise. Side note, if you are going to end up curating something like this, like I almost want to say, you expect the number of people to grow, like get more, not the number of treatments to increase. So if you are going to manually curate something, do the top version, especially in programs like Excel, because Excel has a column limit. Like you will actually run out of columns in Excel if you enter your data sets that way. And a lot of database systems have column limits as well. They don't necessarily have row limits. And that happened last year in the UK when they were entering COVID data, and a lot of their systems went awry because they ran out of columns. So that's just a side note for curating your own data set. Hadley says that for a computer representation for a clean data set, we want this representation. It takes up more space. There's a lot more repeats. It's harder for me as a human when I'm manually curating data sets to do spot checks. But remember that last example I showed you, that group by example? I can now say group by treatment, give me average result, right? I can now say that and run that command, and we know how to run that command. A little bit harder to do that in any of these formats. We couldn't say group by whatever. We couldn't say group by treatment. We would have to calculate treatment mean, then treatment B mean separately. But in this representation here, we can say, here's the column I want you to split. Here's the column I want you to calculate by average, right? So there's a difference between how we as humans would want our data when we're curating and viewing it as a table, and then what the computer needs to run these calculations. And so this portion is about flipping back between these two views of data. So don't feel like you're stuck to one, but hopefully knowing that you can make these transformations, you can curate your data better. Not only can you curate your data better, fixing, like going from one of those views to this one that I have presented, there's a lot of common data problems that we can fix along the way. And so in this paper, they say that what is a row and a column, or how should our data sets be formatted? Each variable forms a column, right? So we should have a variable called name, treatment, and value. Each observation should form a row. So we have treatment values for each treatment across each row. We won't talk too much about the last point, which is each type of observational unit forms a table. That is more like database management and storing data. We won't really talk about that today, since most of the time when we're putting together and analyzing data sets, we're combining tables, not splitting tables. So that's why we're not going to talk about this last point here today. So let's go through cleaning up our data sets. We're going to be concerned with these first 3 points. Column headers are values, not variable names, right? Multiple variables are stored in one column, or variables stored in both rows and columns. And we'll talk and see how each of those problems, you've probably seen these problems in your data sets before. And so we will go through each of these problems and show you how to fix them in Python. And so the very first problem, and I think we will actually go and load up this data set as well, but I'll talk through the problem first, is here's a data set comes from the Pew Research Center for a given religion and income bracket, how many people or families identified for those two variables. So this is really nice in the sense that it's very compact. It fits into our data set, or in this paper, in a very compact manner. But again, the problem is we can't say group by income bracket, give me the total sum, right? So in Excel, you can probably do this. You will select the column and you'll get the numbers at the bottom. But then you'll have a row that is essentially like the sum, right? And then now you always have to remember to not count that one row because you've added a value to your data set that is duplicating all of the calculations from above, and that becomes problematic. Or in Excel, you end up like creating a little off calculation in a cell off to the side. And then you have to remember, like, if you load this into Python, you have to like remove those calculations because they're not part of the main data set, right? Okay, so how would we turn this into a tidy data set? I actually will, when I'm cleaning data, will physically and literally take out a piece of paper, take out a pen or a pencil, and I will sketch out what is the data set I want at the end. And for me, part of it is because I've done this so much, is I want a column called religion, I want a column for income bracket, and I want a column for count, right? I want those 3 columns, and all of those values are here in our table. So in this paper, we want this version of our data set. And now we can ask the question of group by religion, give me the total frequency, or group by income, give me the total frequency. And why I also prefer like these analog approaches is a lot of times, especially if you're very new to programming, you get bogged down with the actual code and you forget like what is the thing you're striving for. Like it's just a lot of it is also like you're juggling multiple things because programming is so new. You might as well put down on paper so you don't have to keep in mind the final form of the data set you're aiming for. And it just helps with like, okay, I just need to worry about the programming part because here I can just look over to the side and that's like the outcome that I want. So this is the format that we want. So let's see how this works in Python. All right, so brand new notebook, right click on the top, go to rename. I'm going to say 02 tidy. And we should, on the side here, have our second notebook. And we will go through the examples for that very first example from that paper, right? So this is a brand new notebook. So just like our first notebook, we have to import the Pandas library. So we'll run import pandas as PD, and we will get our pandas data frame. And the example that I'm going to show you right now is columns containing variables, not values, not variables. Right. And why is that? Is because if you go back to our original data set that we're going to load, less than 10K, those are all values of a variable called income. They're not variables on their own. There's no variable for under 10K. It is a value for the income variable, right? So this is the problem that we're currently going to deal with. So we're going to say PEW for Pew, just like we loaded up a data set before, the Gapminder data set. We're going to run read_CSV. And we're going to say data pew.csv. And we don't need to have the sep parameter because this is a proper comma separated value, not a tab separated value. And you can see here, if I run Pew on its own, this is the data set from that paper. So we're going to actually go and work on this data set and replicate the results from that paper. So in Pandas, this notation, let me scroll back to this paper. Right here, we're going from this data, this version of the data to that version of the data set. Another way you can let me pull up the actual GIF of it. Yeah. So another way you can see these two forms of the data set is we're going from a column called with more columns to a data set with more rows, right? So we are going from data set from more columns to more rows. So we're going from something that's quote unquote wide to something that's quote unquote long. In Pandas, this wide to long function is called melting. Because if you melt something, it becomes long. That's why it was named that way. Technically, it's named that way because Wes named it after Hadley's melt function in R in Reshape 2. That's why he called it melt. And so that's sort of some of the history behind that. If you want, and I'll put in a few more resources when we conclude towards the end of where that GIF is coming from, or GIF is coming from. So we go back to our data set, And the function that we're doing is called melt, right? So we can say dot melt. That's the function that we're going to be using. How does melt work? If you ever get confused, I believe you can put in a question mark. Whoops. A question mark without the round brackets, and you'll get the printout of the help. What I like to do is I put my cursor between the round brackets, and I hit Shift Tab, and I get the help notation as a pop-up. So you can do the question mark notation or the Shift Tab notation to get the help signature, the function signature. So melt, the thing that we need to provide is something called ID vars. ID vars is the column that we do not want to change in this process. So in our current data set, if we look at Pew, the column we don't want to change is the religion column. So we'll put that into our ID vars. So we can say pd pew.melt ID underscore vars is equal to religion. And we can put in multiple values here. So I'll just put in religion. And now if we run that command, you'll notice that all of the other columns that was not specified in ID vars got melted down into the long format. And we now have a variable called variable and a variable called value, or a column called variable and a column called value. That's useful. We can also, at the same time, when we're running melt, so I can hit Shift Tab to look at the other parameters. Value vars, we can specify value vars instead of ID vars. So sometimes it's easier to specify the columns that you want selected versus the columns that you don't want to melt down. So that's where those two are related, and you can see it in here. So the thing that we want is var name. It's called value, and then there's another one called value name, I think. That allows us to set those column names when we pivot, when we melt them down. So we can say var name is equal to income, and value name is equal to count. And now if we run that, we have essentially cleaned up our data set where we have religion, income, and count, right? We'll talk a little bit more about like functions and applying functions, and it'll sort of tease into working with like income, like you can change some of these things. But for now, we'll just work on just pivoting our data sets. And this is nice because we can save this, call Pew, let's call this Pew tidy. We can now do something like Pew tidy group by income, give me the count column, and then give me the sum, right? And now just like before, so this is the total sum for everyone in our data set. Just like how we did mean with the Gapminder data set, we could have also used AGG, aggregate, and then NumPy sum, for example. But this is sort of the faster way at the moment. So let's look at another version of this data set. There is a billboard data set. And we can get that from data/billboard.csv. And this is a data set that has the same problem. And I mentioned this because what is the actual symptom of our data set? If you ever see a data set where it's like week 1, week 2, week 3, week 4, et cetera, like counts of something, like years are really common being stored as columns. weeks like this, income like we just saw. If you ever see a data set where like a bunch of those columns really are like part of the same grouping of variables, that is your cue that you might need to do a melt function, right? I say might need because sometimes it's easier to do certain operations in one format. For example, find me all of the songs where week 1 is over 90, but week 2 is over 85, right? That's a question you can only use in this wider format. But if the question was, what is the average Billboard song ranking across each week for all of our songs, that is a different question. And you will need to do that melting because you will probably need to run that group by aggregate function. And so there's uses for each of these formats, and it's very important that you identify which of these transformations you need to do. And so the Billboard data set is essentially the other, like the bigger version of the income data set, except this time our ID values, right, the columns we do not want to change, is year, artist, track, time, and date entered, and then we want to pivot everything else. So let me paste in that, and so there you go. So we have the same problem. We have our Billboard data set we're going to call melt, and so now in melt, our ID vars is going to be multiple things. So it's not just income anymore. It's now the year column, the artist, track. I'll paste this for you guys because you don't have to type all this. Date.entered. And then what is the other parameter? Value name. We'll call it rank, like what is the Billboard ranking? Sorry, value, var name. Week. Right, so I'll paste this so people don't need to type all of that. And so this is how we can pivot that data set down, and then we can run the same thing like group by week, give me average rank, if that's the question that we want. All right, so that's the problem of what happens when our columns contain variables. Let's go back to this paper. There's another very common data problem that we end up having, and it looks like this. This comes from the WHO. It is the count of tuberculosis for each country year. And then on the columns, we have M014 standing for male 0 to 14. We have all the way up to males unknown. And then we have the same sets for females that's not shown in this data set. And so this is a data set that's really common, especially if you're downloading data from, I definitely know from like the CDC. They end up having data that's grouped like this, like all just frequency counts. And so the first thing we'll notice is we have the same problem as before, or let's go back to our analog paper format. What is the data set that we want? We want a data set that has country. We want a data set that has year. The problem is this 0 or this 2 actually has this cell, or like that value is counting for 2 variables, right? It's counting whether it's a male and its age group. And that's a problem, right? Because this is the second problem in our data set where rows are being, columns being having 2 variables associated with it. And so when you're curating your own data set, you'll want to make sure that like each thing only counts for 1 variable. So we want a column for the gender, and we want a separate column for the age group, and then we want a column for the actual count. So we can work in steps, one of the first things we notice is the same problem we saw before. Like, hey, these columns, I'll even be okay if I get a column that is gender age, right? That'll get me a little bit of the way there. And so we can do that. If we melt down our data set, we'll get this data set on the left, gender age, and then count. And then if my question to you was, how do I separate gender from the rest of it without even thinking about programming, you might say like, hey, take out the first character. That first character is going to represent, in our case, sex, and the rest of the numbers is going to represent age. And then we can do that. And so you can see, like, once we did that pivot, that melting step, we can then figure out the next step that we would need to do. So let's go through this data set in Python. Let me actually go and copy this because that's the part that we're doing. And so the problem, the data problem that we currently have is variables are stored in both rows and columns. Actually, no, that's incorrect. That's incorrect. Hold on, that's not the problem. Multiple variables stored in one column. That is the correct title. The one I just typed is the next example. So instead of that data set, we have another data set. It's the Ebola data set. Read underscore CSV data slash E. It's not called Ebola. It's called country time series. So this is a data set that was curated by Caitlin River. She was a PhD student at Virginia Tech before I came in to my program. She's currently working in Hopkins, Johns Hopkins University. And she curated the 2014 Ebola outbreak. She put together this data set. Essentially, when each of the countries were doing their reports, she was kind of curating it into one giant data set, and that's the data set we are looking with right now. So you can see that this data set has the same problem as before, the example I just showed you. This 2,776, what does that represent? Well, it represents two things, whether or not this is a case count or death count. So let me show you the Ebola.columns. You'll see that we have cases Guinea, and then we also have the deaths Guinea, right? So this is a number that represents whether or not this is a case count or a death count for a particular date and day of the outbreak for that particular country. And it also tells us what country that case or death count is, right? So it's the same problem as before. This number represents two things. So how do we fix that? Well, we fix it in steps. So the first step that we'll do is we'll run the same melt command. So a lot of the data problems probably will involve melt. And so that's probably the first thing that we'll do. So we'll use melt. So we'll say ebola.melt and ELT. And the ID vars are going to be those first two columns. One is called date, and it's a capital D, and day, capital D as well. And then, since we're cleaning up our data set, we can say var name is, let's say this is case count, death count, country. And then our value name is going to be count. So we're almost the way there. We have case count, death count, and country, and then a variable called count. So let's save this into a variable. We can save this to Ebola underscore long because it's got a lot of variables, got a lot of rows. Oh yeah, thank you for pasting in that paper. I will put this in the README file at the end of the class, so it's also there. So we're most of the way there, right? If I were to ask you, sorry, let's look at this data set. If I were to ask you without even considering like how to program it, how would you split out the case count, death count from the country? You'll notice that there's a very convenient underscore there. I mention this because as you're curating your own data set, it is also okay to leave like underscores or dashes as a splitting marker, right? Because the way we're going to split case count, death count from the country is by splitting on the underscore. So a little bit more about Python and how strings work. So let's say we have a string called SciPy underscore 2021, right? So here is the string. This part has nothing to do with pandas. Given any string object in Python, they have their own methods, right? So just like how our data frame had .info round bracket, strings have their own set of things that you can deal with strings, like finding string, getting subsets. One of them is also a very convenient function or method called split. We can tell split, what do you want to split this on? We can say underscore, and now we get two values back. And just like using square brackets that I told you in that first hour, we can use the square bracket to get different parts of the splitted value, right? So we can get the 0 index because Python starts counting from 0, or the 1 index, or that, or the second thing. So another question I got was, you notice that like variable names like date entered, date dot entered here became in our data set, it has a, oh, that was like up here, a period in it. So it's not a problem, this period, if you are, so I didn't show you this. A part of it is because of teaching. So you can enter, you can select column names like this using this square bracket notation. What you can also do, I think it's, what is it called? Time. What you can also do instead of the square bracket notation, sometimes if it's not already a attribute, you can use the single dot notation as a quick way to pull out a column of values. But you have to be careful that you don't have a column called shape, because that might be a case and it'll give you the actual shape. So this comes into play because I can't say date dot entered because that's not going to be a thing, right? So I have to use the square bracket quote notation for columns that are weird. This includes columns that have spaces and all of that. So that's the only part where it'll give you problems in Python is if you get lazy and you use the dot notation to pull out columns, then you can't if the column name has a dot in it. So there's a library called Janitor that Eric Ma, who is also part of attending conference, he wrote the janitor function, he ported over the janitor library from R, and one of those functions is called clean columns, and it'll remove all of those dots and uppercases and all of that stuff, and make them all lowercase, and all of those weird symbols become underscores. So that should help with things. Okay, back to string splitting. This notation here, where I have a string and I'm calling the split and I'm telling it to split on whatever, we can do this in a pandas data frame column, right? So we have our Ebola data set, Ebola long, right? Just because you brought it up, I can say dot cd underscore country, right? So I'm just pulling out the cd country data set, right? So instead of using that square bracket notation, this is one way. It's just a little quicker. There's some ramifications. They're not exactly the same, but for the most part, you can treat them both the same. So we want to be able to run dot split just like before. But we need to access this column and treat it like a bunch of, let me see what the words are we want to find. We want, since we know that this is a column of strings, part of it is because it's object, the D type is object, we want to access all of the base Python string methods on it. How do we do that? There is an accessor, just like LOC, ILOC. There is one called str for string. And now we have access to all of the string methods on this column. So we can treat each of these as individual strings, just like before, SciPy 2021. And then we can say we're going to call the split function and split on the underscore. And now if we run this, you see that we get the same results as before, right up here. But now instead of writing a for loop, if you've programmed before, it will do everything down the entire column. And so when I also talked about the very beginning about a data-centric approach to learning Python versus a programming-centric approach, you can actually pull off or push off learning about loops when you are working with data, because for the most part, every operation works on every value in a column. And so you can get away with teaching loops. So we have, this is part of the way there, right? Now we just want the first part for one thing, the second part for the other. Ebola long. Yes, let me paste this. Right, so we're almost the way there. Let me save this to a variable, just so it doesn't end up being a super long piece of code. So the next thing we want to do is pull out that first object for cases and pull out the second object for the country. So how would we go about doing this? So if I have the var split, I can run str again to get access to all of its components. There is another parameter called get, and we can give it the value 0, like get the first object for each list object in here, and you will get all of the cases or all of the debts for that data set. Right, so we split everything using that underscore, and then we can access it again using the str and get methods to pull out for each one of those lists, get the 0th index or get the 1 index. And so what's left is we can take this and either save it to a variable, or how do you create a new column of variables in Pandas? Well, you essentially pretend it was there the entire time, and then you assign it that value. So we can say Ebola long, and we can say country. Pretend the country column was always there, and assign it that. And so now we can do the same thing. Instead of getting the first thing for country, we can get the second item or the index 1. Oh, sorry, it's not country, it's case status. We'll call this status and then country. And then we have properly split out the CD country data column into the separate part for country and a separate part for its status, right? And so the key thing in this part was not only did you have to melt your data set to get it into long format, but then using whatever heuristic it takes for string manipulation, you can use the str to get access to all of the string stuff in Python. So you can look up like string methods in Python, and all of the split, find, match, all of that stuff applies here. We use split, and then we got those individual components, and then assign them back to our data set. And the way you create a new column, again, pretend the column was always there, and then you can assign it that way. And now you can, do your thing. Group by country, group by status. Give me the total count, right? So I keep bringing that up because these are all of the data manipulations that you would have to do to answer like those stats questions. Or we'll talk a little bit about fitting a model at the very end, but that's how this all works. Right, so let me copy all of this so you have it. All right, so I'm a little bit behind, but let's talk about the last data problem, and then we'll take a longer break because for some of us it's lunchtime, and it's also been like an hour almost. So the other question was like, how do we get rid of CD country? Two ways to do it. You can use del, like delete. I typically don't use that because it's you have to use the square bracket notation for del. But what you can do is in equal along, there is a method called drop. And then in drop, if you look at the help, so you can say shift tab, give it the label, but you also have to give it the access. So you can say single label. So we can say CD country, and then we can say drop by the column. So we can put in CD underscore country, and then access is column. Is it column? Columns. Goodness. Columns. And we'll get that. The thing to remember here is you have to reassign the variable because equal along itself was not changed in that case. So if you really want to drop it, you have to remember to reassign it if that's what you want to do. This last part here, like reassigning it, ends up being something that you forget very often. There's another parameter in here called in place. It's set to false by default. So if you set that to true, you don't have to do this part here. It'll do it in place. But I typically end up just reassigning it that way. So you don't accidentally do something and drop a column that you didn't mean. So the other question is, can you change the type of the numbers that are being displayed? So instead of float, like these should probably be integers. The answer is yes. So for every column, there is a method called as. So you can say like count, right? So that's all count is an actual method. So you can say count, and then each of these columns has an as type. And you can give it like int. Or so you can convert it into like another type because numbers have like an NA value. We're not really going to talk about NA values. There's another one. There's a version that is like pandas convert number. It's called 2_numeric. Yeah, so there's like a 2_numeric, and you can turn that into what is it? Oh yeah, downcast. So you can turn it into like an integer or something. So if you're working with numbers already, you use 2_numeric. Otherwise, if you want to turn it into like a string, you can say like as type string. So I'm not going to do that because I don't remember the actual notation for it right now. So, but you can do it, I guess, is the main takeaway. All right, last part. I'll go through this last part a little bit quickly. So this one is the problems where variables are stored in both rows and columns. What does this look like? Typically, you can't actually tell that variables are being stored all over the place. So here's an example data set. This is data sets where some expedition for a particular location, year, month, they are taking for some day of the week, they are taking temperature readings and giving a temperature max and min. So I know that the example title is for being stored in both rows and columns, but at first glance, we still have the same problem as before. We see D1, D2, D3, et cetera, probably a melt operation because we want a column, again, that says day of the week, and then value, right? So we have ID, year, month, day, element, and temp, right, for temperature. That's the data set that we want at the end of the day. So let's go and fix that part of the problem. Fixing that part of the problem first requires us to load up our weather data set. So let's load up our weather data set. We'll call this weather is equal to pd.read_csv and then data/weather.csv. And this will give us the same data set that we saw from the paper. We'll see a bunch of NaN for missing values. That's totally fine. We won't talk too much about missing values during this workshop because it's I'm trying to teach you like the things that are more conceptually difficult, and then a lot of the other stuff you'll learn as you work with data. And so usually, also for time, this stuff is probably more useful for most people's time in terms of talking through the concepts of how to manipulate data, and everything else ends up being like details of that stuff. Yeah, so this D1 is day of the month, right? So it's not, I have no idea what else people were interpreting it as, but yeah, the D stands for days of the month. So we have the same problems before. So let's not worry about like this data set is super messed up. Let's just fix what we can right now. So we can run this as weather_long is equal to weather.melt, right? So a lot of things will end up using melt. We have the same function call. So ID vars, what are the columns we want to hold the same, like not pivot? So ID, year, month, element. And then since we're processing and cleaning our data, we can put in var name is equal to day, and then value_name is equal to temp. So this temp means temperature, not something that's temporary. So the other thing here that you'll notice, so we pivoted that thing into the long format. One thing in this current example, because we have a whole bunch of missing values, we can drop all the rows. If any of the values have missing, we can drop the entire row. So we can run drop NA. Yes, there's more what's the word I'm looking for? There's less violent ways of dropping missing values, but for this example, just so we don't have a bunch of NA values at the end, and we know that everything is, we just want to look at the values that are all complete, we'll just drop all of the missing value, all of the rows that contain a missing value. So I'm going to save this So we have weather with the missing values dropped. And so now, if I look at this data set, this is how you know you have an additional problem that's kind of going on. If you ever end up in a situation, so let's look at these two values right here. If you ever end up in a situation where a whole bunch of values in the row are duplicated except for like one value or one or two values, you probably have this problem of values being stored in rows and columns. I forgot to copy that, so there we go. So ideally, now that we're looking at this data set, maybe so go back to that paper. What is each row observational unit? Like, what is the thing we're trying to measure? We're trying to measure the temperatures for a given month and day and year in our data set. Do we want that observation? Like, that unit should be year, month, and day, right? We want the row to also be what is the minimum temperature and the maximum temperature. So we need to do the opposite of all of the melting because we want to specify, hey, we want a column for Tmax and Tmin, and here the temp column is going to serve as the values. And this is essentially very similar to the pivot table function in Excel. It's also called pivot table in Python because it pretty much is the pivot table function in Excel. So the function we're going to use is pivot underscore table. And in here, instead of ID vars, there's a column, there's a parameter called index. Index essentially behaves like ID vars. These are the columns you do not want to change. So we're going to say index is equal to ID, year, month, day. The next two things that we want is the columns argument. So we specified ID, year, month, and day. Any of the other columns that we don't specify, so we haven't specified element and day, element and temp yet. So in columns, we're going to say, hey, this is the column that we want to pivot out. So each unique value in here is going to be its own separate column. So we're going to get a column called Tmax and a column called Tmin. So we're going to specify that here as element. And then as it's doing that pivot back up, what is the column that we're using for the values to fill in the table? That's values, and we're going to give it our temp column. And I'll paste that in for everyone. And so now, again, you see this weird printout, just like before when we did that multiple group by. So first thing to notice, this is some hierarchical structure in our data. So it's, but it's got everything that we need. So first things first, let's fix this hierarchical structure. Remember what I told you, put everything in round brackets. And then reset underscore index. And then we can put that on its own line, put that on its own line. And I will copy this for everyone. And so now you can see after running that reset index, it collapsed everything and made it really flat. So now we have a regular Python pandas data frame object. And then everything that I've talked about can apply. So if we want to filter and select rows, select columns, all of that, nothing different from that first hour. And that's all from resetting our index. And so now we have, for each row, it is a year, month, day, and then Tmin, Tmax. And then for the day, we can clean this up very similar to before using that split, or we can treat this as a string and remove that D if we want to. I'm not going to cover that, but that's how that stuff works out. All right. So I went a little bit over the hour thing. So let's take a longer-ish break. So come back at 35 to the hour. Let's say that. I'll give you like 12 minutes. 35 to the hour. And we'll talk about writing functions and stuff. And then whatever time is left, how everything I've showed you today fits into like fitting a statistical model in Python. And so I'm not going to try to teach you statistics, but I'll show you the mechanics of how scikit-learn works. And then depending on what other tutorials you've taken for this conference, hopefully that all meshes together. So come back at 35 past the hour and we'll continue with the rest.
Daniel, do you want to hang out here and answer questions or take a break?
Oh, sorry, 35 of the hour. So like for me, it's going to be 12:35. So figure out your time zone. So it's whatever hour of your time, and then the minute portion is going to be 35.
So do you actually want to take a break and go offline or be online and answer questions?
All right, hello. Hopefully my stuff is all working and my screen is still being shared. One of the questions from the Q&A was, how do you install something from the Windows command line? If you have Anaconda installed, you should have the Anaconda terminal. Don't mind me, mine says MiniForge, but you will have the one that says Anaconda prompt. Here, you can run the pip install or the Python -m pip, however you want to install your packages. That's how you would do it. And that's if you're on the Windows side. From the Mac and Linux side, as long as if you have the Anaconda version installed and you see that word base, that means you are probably in the Anaconda distribution, and you can Python pip install from there. I think that's all of the questions. All right. All right, so we're going to open up a new data set, new notebook. And right now, we will call this 003 functions. All right, so this is going to be a little bit about like Python from a programming perspective. We're going to talk about functions, and then we'll see how these functions that we write can work on our data set. And again, this is really, this talks about like the ordering of things, because even though we can have a function work on each row of our data set, we don't have to write for loops. So in general, if you're working on the data frame itself, it's very unlikely you will ever need to write a for loop. There's always exceptions to that rule, but you shouldn't have to manually loop through rows or columns of your data. So how does functions work in Python, and then how can we use them in our data frame? So first thing about functions, what does the general structure of a function look like? In Python, it begins with the def command. We're going to define a function, and you'll notice it turned green. So that's another thing. Do not name any variable called def, because it is something that's important. I'll give my function a name called my function. It's going to have a set of round brackets. It doesn't take anything inside, and we'll currently have a empty function, and I'll create the empty function by passing in the word pass. That just says, here's a function. It takes 0 arguments, and it doesn't do anything. So this is the general structure of a function. So let's write a function that does more, that takes more things instead of just an empty function. We can define a new function. So pass here. Oh, so a little bit more about the function layout of the function syntax. After the colon here, we have to indent our code, and everything that is in this indentation is part of this function's definition, like what it will do. Since we can't leave it empty and we want to have it, or for me, I want it to do nothing, pass is the Python word for pass. Don't do anything. So this is my way of writing, here's a function that literally does nothing. And since I can't have a function that is empty, right, it's expecting an indentation block, and you can't have it being empty, we just put pass to say empty. So I'm going to have a function called mysq for my square, and in here, I want the function to return a value. So we say return, and then what is the thing that it's returning? It's going to return x, like the input from here, x. And how do we exponentiate in Python? We use 2 stars. So single star is multiply. So if we said x star 2, it would have been x times 2, but x star star 2 means x squared. So now we can say my SQ and give it a number 4, and it'll return 16. Cool, so that's our first function. One of the things you want to do every time you run a function, and if you ever are running this like visual check, you want I'm going to slowly teach you what it means to do a unit test. Whenever you run a function that you wrote yourself and you're doing this visual check, oh, mysq4 should give me 16, you want to program that into your file somewhere such that if you ever make a change to this, you know that that visual check is programmatically being checked as well. So how do we write this visual check as a programmatic check? We use the assert statement, and we can say, hey, my square of 4 should double equal to 16. And now, if I ever run this code again, and if nothing happens, everything is great. If, for example, I change this function and I don't change this assert function, it will actually throw an error. Right, so this is a great way if you're doing these visual checks. Well, if you're doing the visual checks, you're probably writing the code anyway. And if you're writing the code, all you need to do is write the assert statement. And as long as this doesn't return anything, that means that that statement is true, and you'll only get an error if that statement is false. And that's essentially the beginning of unit testing. So the other question again was, what does pass mean? So pass literally means do nothing. So occasionally there's going to be some kind of way where you want Python to see something and then just skip over it. That's why pass exists. In our case, I'm using it as like, here's a function that literally does nothing. Okay, so let's write a function that's a little bit more complicated that takes 2 parameters, right? So the read CSV was a function that took many, many parameters, not just the input, just the file name. So we can define avg2, and the way we put in multiple parameters is in the set of round brackets, we put in a comma separated, essentially, what variables are going to go into that function. And so how do we calculate the average of 2 numbers? we can return x plus y, and that result divided by 2. And these function definitions are important in the sense that we're going to end up using them. So I will paste them along so you have them. But remember, and it's not showing up when I paste it, you do need this indentation right here. That is part of Python syntax. Okay. Yeah, so I didn't actually use this function. If you want, you can actually call it, but it won't do anything. And this was mainly just talking about the actual function syntax. Other things you can do with your function is inside the function parameter, you can use a set of 3 quotes, and it will. This is how you create a multi-line comment or multi-line string in Python. And in here, you can write the actual function comment or the what does x take and how does it work. And if you do that and you run, and it's important you actually run this code again, if you now do $average2, it'll give you the signature and then that bit of the text, right? So all of that like cool stuff that we see when we run like shift tab or ask for help, that's literally in between these sets of triple quotes. And so, you know, a lot of the stuff that you see in Python are not actually as complicated as they may seem. The length of the indentation does matter. The Python, official Python PEP 8, like style guide says use 4 spaces. You can use 1 tab as well, but it's be consistent is the actual key. I use 4 spaces. Most of the time, these IDEs will default to 4 spaces. So that's what you want to end up using. You can set it up where a tab ends up being 4 spaces, so you can use that as well. Okay, so I wrote this average2 function, we gave it the syntax, and then we can actually use it like, what's the average of 10 and 20, and it gives us 15. So how does this apply to pandas? So let's import pandas. We'll load up our data set, import pandas right now. I'm going to paste in this little block of text so everyone has the example data set that we'll be working with. And I won't call it df, so actually that was me copy and pasting from the wrong side. So let's call it dat so we get out of that habit of calling things df. And so this is how we create a Python data frame manually. Essentially, these curly brackets is like a Python, not is like, it is a Python dictionary. It has a key, which represents the column name, and then a set of values. So we can say like, hey, A has these values 10, 20, 30. B has these values 20, 30, 40. And we're going to put that all together to create a Python data frame object. It's kind of rare, depending on like what part of the data pipeline you're coming from, to manually create data frames like this, but something you can do as you are starting to programmatically curate your data sets. So we have our data set dat. So a lot of these data sets in Python, in pandas, a lot of the mathematical operations are broadcasted. So that's the actual term called broadcast. You might also hear it as vectorized. And that means that if you give it a column or a series or a vector of values, and you say like, hey, add 1 to it, it will know to operate on each individual item one at a time. What does that mean? So let's say I have dat of the A column, right? 10, 20, 30. And if I say, hey, go square yourself, it knows to operate that squaring operation on each individual item, right? It knows, like, here's a vector of values, here's a series of values. Add 1 to yourself. It knows how to handle that. This notation here, we can use it. We already wrote our own squaring function up here called my square, right? So how do we use our own custom function? We get our data frame. We give in the column that we want, right? Our squaring function takes in one set of values, right? So if we go back, it's my square of 4, right? It takes in that one value of 4. And we want to put in 10, 20, 30, one at a time. The way we do that is we say dot apply. And then we give it the function. Notice that we're not giving it the function with the parameters that we're putting in. We're just giving it the actual function. And it knows to put in, okay, the function is my square, I'm going to put in 10. I'm going to put in 20. I'm going to put in 30. And that's why I say to all my students, you should almost never write a for loop when you're working with data frames, because everything is an apply function. All right, so what happens if we want to use a function that takes in multiple parameters, right? So we can define my exp, like my own exponentiation function. So we have our base and our exponent. I think that's the correct terminology. Mantissa, I think, is the actual thing, and the exponent. So we want to return x star star e. Right? So now we can write our own kind of exponentiation function. So I can say assert my exp to 10 should equal 1024, right? So again, always write your own programmatic checks. And this is literally how all the big famous, like this is how we actually do like unit tests. It's literally a file that is nothing but a series of statements. And yes, apply is preferable to loops, and for the most part, it is going to be much faster. That is a true statement. And part of that is also because it's leveraging like certain optimizations like under the hood and stuff like that. If you look at the source code, apply is writing its own for loop. Like you are never going to not have a for loop in the pipeline of things, but apply is written in such a way where it is a little bit more optimized. And it's also easier to parallelize the apply with Dask than it is to write a for loop. Parallelization in Python is kind of weird. So use apply when you can, because it converts into Dask and multi-distributed parallelizations much nicer. All right, so now we have this other function, so we can do the same thing. Instead of applying my square, we can pass in my exp, but now the problem is, how do we pass in that e, right? Let's say I want to take all my values and raise it to the 4th power. So the way we pass in other parts of our data set is we simply, again, pretend it's always been there. So we can say e equals 3. And now we can take the cube root, not the cube, we can take the cube of all of our values. The trick to this is the thing that's getting passed in from our data is the first parameter of our function, right? So if we wanted to do it the other way, we either have to rewrite our function so the first thing gets passed in, or you'll see something like this where people are let me think. Let's say I want to pass in my 10, 20, 30 as the exponent, and I want to keep like the same value in the beginning. So this is where you will either rewrite your function such that you're flipping the e and the x, or you'll see people write something like lambda, let's call this a, and then it'll be my exp, let's call this 3a, right? So this will now, this is the same thing as rewriting my function and flipping the components. But now I'm saying, hey, each value is going to come in as a temporary value called a, and I want to pass it into this other parameter by keeping 3. So it'll be 3 to the 10, 3 to the 20, 3 to the 30 if power, right? So you'll see that type of notation pretty often. For the most part, if you're super confused with this lambda notation, what I would do is take this and rewrite it such that e comes first and then x is the parameter you pass in. The question was, why doesn't my assert work? It does work because it's true. If this was not true, it will error, right? So we know 2 to the 10 is 1024. So that is a true statement. So it will pass. And if the assert statement passed, nothing will happen. If the assert statement doesn't pass, you'll get an error. And so that's how you can run your code. And if the assert statement passed, you know that something is wrong with your function, and you can stop and fix that before it takes like the 3 hours to run the computation. So this lambda statement, this lambda statement is essentially writing a function on the fly. And I mention it because this is something that you'll see pretty often. So I can call this flip exp and call this e and x, right? So one way, so what happens if the function that I wrote, I want to pass in the data from my column into the second argument and not the first one? Because by default, it passes it into the first argument, right? There's no way to say like, hey, I actually like this a, I want it to be treated as the e instead of the x, right? There's no way to do that by just using apply. So one way you can do it is rewrite it, and then it is essentially doing return my exp x and e, right? And so you're flipping the first parameter because you want to apply it to your data set. So one way you can do it is running flip exp and then x is equal to 3. Right? So that's one way you can do it. Some people don't want to rewrite the function, and they want the function to be created on the fly without doing this defining part. And that's what a lambda function is. Lambda is literally saying like, here's a function, it doesn't have a name, right? This function here has a name called, if I typed it right, flip, it has a name called flip exp. And this one down here doesn't have a name. It just has the function definition, which is my exp 3a, right? So these are two ways of doing the same thing. I used to not understand how lambdas work, and I would just rewrite my function, flipped around to the way it works, until eventually, once you get used to the apply statement, this statement here will make sense one day. It doesn't have to be a. It doesn't have to be the same thing here. I could have called this like, maybe I should have called it, here's pizza, because I'm from New York City. So yeah, it doesn't have to be the actual column name. It's just showing you that here's a function that I'm creating on the fly, and then reusing my original function and placing that thing in a different location. That is something that happens pretty often because not everyone is just like, oh, I'm gonna pass in from a loop on the first item for the first parameter, right? Okay. Where am I? All right, so that's how the apply works on series objects, right? So remember, series is a particular column in our data set. For the most part, you only want to work on columns in your data set. But let's say we want to work on our entire data frame object all in one go. I'm going to write a function. It's going to not make sense until I start to use it. So I'm going to write a function, and all it does is whatever you give me, I'm going to print it out. So if I give it 3, it's going to give me 3. And the reason why I'm writing the function this way is because now let's say instead of a single column of data, so I can always have written dat of A and then dot apply print me, right? This part kind of makes sense. That's the same thing, calling the function from before. But now instead of the A column, I'm going to put in the entire data set. And so now you'll notice that when you apply a function to a data frame, what's the first thing that came out? 10, 20, 30. Well, that was column A. Next thing that got printed out, 20, 30, 40. Well, that was column B. Because there was no return statement, I got 2 none values, or like nothing got returned. So that's what the output of the thing was. But you'll notice when I apply a function to a data frame, by default, it operates on each column. So it goes column-wise by default. So let's write a function that takes 3 values and calculates the average. For this data set, let's say I want the average for each column, right? So let's define a function called avg 3 x, y, and z. And this returns x plus y plus z, and the whole thing divides by 3, right? And we can test this. So assert average 3 of 1, 3, 5 should equal 3. And great, that works. So now let's apply this function to our data frame, right? Because like I said, our data frame, it works column-wise, and we want the first column of 10, 20, 30 being passed into our function here. So now if we write dat.apply average 3, we will get an error. Part of this error, if we look down at the bottom, it says missing 2 positional requirements y and z. So why do we have this error? It's saying that you didn't give me a y and z value. And it's because when we apply things on a data frame, that entire column, the entire column, like 10, 20, 30, is being passed into the first value in our function. So 10, 20, 30 is being passed into x. And that's why nothing got passed into y and z. Right, so that's one very important thing with using the apply function, is whatever thing you're applying into is getting passed in. All of it is getting passed in to the first parameter of the function. And it's all being passed into x. That wasn't a problem when we were working with the series because it was only one value. But when a data frame, it's the entire column coming into the first parameter of the function. So how do we fix this? There's a few ways we can fix this problem, right? One is to use a function that already knows and can understand multiple inputs and making the calculation, right? So mean, we know from NumPy. So if we import NumPy as NP, we know that NP has the mean function like we did in the first hour, or somewhere in the first hour. So we can say define average AVG3 apply. It takes the entire column, return np.mean of column. And then we can say dat.apply average 3 apply, right? And then we get two values, 20 and 30, because A, 10, 20, 30 was passed in, and then B, 20, 30, 40 was passed in. So we get those two values back because it's working column-wise. So there's a few ways we can do it ourselves, right? If we wanted to have the same functionality ourselves, we would have to take this parameter and rewrite it. We would have to rewrite it in such a way where it takes a single value. So that's how you deal with applying functions on a data frame. If you want the function to run across all of our columns, right? You have to rewrite it such that it only takes one parameter, and that one parameter is the entire column of values. And sometimes that's tedious. We don't like that. So I'm going to show you how we can avoid doing that. But let's say, for example, I showed you apply. This says average 3 apply. So if we rewrite our function, so let me just paste this. Part of it is for time's sake. So if we want to, we can rewrite our function such that it takes in a single value. So the 10, 20, 30 from column A all comes in as column. We individually parse out 10, 20, 30, manually run the calculation. Yes, it's not just 3 numbers anymore. That is true. It should just be average apply, but I wanted to show you the difference between these two. So we are going to rewrite our function. So it's actually proper average 3 apply like this. And now we can run the same function and it does the same thing, right? So running this average 3 apply. So note that I'm overwriting our function. So by default, apply works column-wise. We can change the way it behaves by saying axis is equal to 0 for index or 1 for columns, 1 or columns. So axis is equal to 1. I don't know why it's columns on the other axis, but you don't, first of all, we'll get an error and it's going to say 2 is out of bounds, because if we do it the other way, so if we remember our data set, we can operate row-wise, and our function here, z, doesn't have a third thing. And so when we try to say, like, what is the index 2 or the third element of this entire row, it doesn't exist. So we can change the way it operates, but typically this axis 1, you don't want to do. It's very rare that you want to operate on your data on its entire row. You also have a huge performance hit because everything, when you do run axis is equals to 1, Pandas and through applied needs to convert everything into the same data type. So now you're also implicitly adding a data check and data conversion in between your steps. And also, typically, you don't operate row-wise on your entire data. Most of the time, you only care about a couple of columns or observations in a row, not the entire row. And if it is the entire row, maybe if it's all sensor data, then you'll probably be working in the matrix style of things, in which case that's a NumPy operation, and that's fine. But in Pandas, because a data frame has mixed data types, that's what gives it its power. You typically don't operate row-wise unless you are completely sure you know what you're doing. But it's one of those things of like, am I actually treating my data or doing the step in my data correctly or in the most optimal manner, typically you don't use axis is equal to 1 when you apply something. Okay, so now let's talk about functions that take in 2 parameters, but we actually want like pairwise from 2 different columns, right? So here's our data set, 10 and 20. Let's say I want to add these, I want a new column called C that is 10 plus 20, and then 20 plus 30, or 30 plus 40, et cetera, et cetera. In our case, actually, instead of adding, let's take the average. So let's write another function. Oh, sorry. Let me step back. If it's all numeric or numbers, we can always run these calculations without writing a function, right? So I showed you data of A. We can do this by saying plus data of B, and then dividing the whole thing by 2, right? This works because pandas and NumPy understand when you are working with series or vectors, it knows to broadcast the operation. So this is known as broadcasting. But let's say we have a function that, like, if the first value is 20, give me a missing value back, right? Or something with a special case, like if, you know, the person is under 18, like give me a missing because like they shouldn't be in this study group or whatever, right? So maybe you have something more than just simple arithmetic. So let's write another function, avg. We'll say average 2 mod x and y. And so a little bit about Python, let's write a conditional. So if x is equal to 20, I'm going to say return numpy.missing, right? So NaN for missing. Otherwise, give me x plus y divided by 2. So this is a special, it's a function that's doing more than just blindly adding and dividing by 2. It's actually doing a check in here, right? So now we can say what we want to do. Most of the time when people run apply axis is equal to 1, what they want to type is average 2 mod df a df b. This is what most people want to do. Take the column A, take the column B, and then pairwise add that stuff in. So I told you before, like if that was the case, this is probably why sometimes people write for loops, because they want to loop through like the index for each row. But there's a much better way of doing this. The syntax is going to be a little wonky, but we'll talk through it. So there should be already, we should have already imported NumPy. So we want to take this function we just wrote, and we want it to understand if we pass in a column of values for A and B to automatically iterate through them one at a time, right? That's called vectorizing the function. And we want our function to be vectorized. Luckily, in NumPy, there is a special function that can help us vectorize our functions. So in NumPy, there's a function called vectorize. Its input, the vectorized input, is another function. So this is a really special function where its input is another function and its output is the vectorized form of that function. So we can say avg2 mod vec is equal to the vectorized form of our original function. And once we told NumPy to vectorize our function, we can now work on our data set the way we expected. Right? So there's no reason to write a for loop. Typically, write your function like normal because it becomes easy to unit test, right? We can write our assert statements and all of our stuff like that. And then all we say is, hey, I'm going to pass you like a bunch of data, and that data is coming from a data frame. You're going to have to learn how to operate in a vectorized manner. Well, NumPy knows how to do that for us using this vectorize function. We get a new function. We didn't have to write anything or change our original function. We use NumPy to vectorize it for us, and it gave us our results. So yeah, one of the questions was like, if it's in tidy data, there should be almost no reason you would operate on an entire row. So yeah, so that's sort of a thing. Oh, that's because I should definitely be dat. And that's because I typed it wrong in the beginning, and let me just, yeah, it's because I typed it wrong in the beginning. Yeah, so it should be dat. So I am also trying to break my own bad habits, but yeah, so you guys should, everyone here should also not use df because it does mean like something else in other functions. So that's cool, right? We don't have to modify our own functions. This notation here, right here, there's a shortcut version of it. So I'm going to copy our original code. This is our original function. I'm going to, just for this example, I'm going to give it a different version so we can separate the two versions. So you notice that the previous example, I had to define my function, then pass it through MP vectorize, and then assign that to a new function that we use later on right here. We can do all of that in one step. During the definition of our function at the very top, we can call NP vectorize using this @ symbol. It's called a decorator. This will take NP vectorize, call it around this entire function definition, and reassign it to the definition we gave it. So this notation, this decorated notation here, is doing the same steps as before, just all in one go. And so that's what a decorator is. A decorator is a function that takes in another function as its input and then returns a modified form of that function. So I'll paste it in, just make sure you have the indentation all correct. And now what that allows us to do is we can now call avg2mod, and we can call dat a and dat b right away. We don't have to do that intermediate step. Yes, and it's outside the function definition. It's the @ symbol above the function, and that's how it knows how to call it. That's just sort of the Python syntax notation of it. And so that's how that works. Yeah, so once and this is how Python like parses the code. So it understands like, oh, this is a vectorized, you're calling me as a decorator. So it knows the function that's being defined afterwards to wrap it and then vectorize or use whatever vectorize is doing. There's many other decorators. This is probably the first one you have seen if you're new to Python, but you'll see other decorators as you go through Python in the data science world. For me, this is really the only one I ever use. But you might see, especially a lot if you're working with like web trafficking stuff, you'll see that pretty much used all over the place. You can have multiple decorators on a function. So I don't know exactly what the syntax is, how that's called. But yeah, you can totally do that. All right, so one last example before we move on. Let me make sure I have this. Oh no, I don't have number. Oh boy. Okay, I don't have number installed because I guess I realized it's not part of the Anaconda base installation. So I'll just show you the example. If you are predominantly or exclusively working with numbers and your function is doing a numeric computation, so in our case, all we're doing is checking if it's equal to 20, return missing, otherwise perform some numerical computation. All right, let me make this a little bigger. So this part of the function is no different. Numba is a library that is highly optimized for numerical computations. So instead of numpy.vectorize, you might get some mileage using numba.vectorize, and you call it the same way, except remember in the first hour where I told you the three components of a data frame was .columns, .index, and .values, and the .values is the numpy array representation of your data. Because Numba is super optimized and it only understands NumPy arrays, you have to call it with the actual NumPy array version of your data. So that's the only difference if you're using Numba vectorized, and you get the same results. In your actual Jupyter notebook, you can run %% time it, and you will actually see that simply using numpy.vectorize will give you like a pretty good speed benefit. And then if you use Numba, you pretty much can get like order of magnitude speed benefits if it's all a numerical computation, essentially for free. If it's not for free, then it didn't really take you much effort. All you did was say at numba.vectorize at the top. And so it's a very worthwhile check if your function is doing nothing but numeric computations. And that's how you can use decorators, how you can write functions and apply your functions to your data set without using a for loop. And this is pretty much like what I see, like most people who are very new to working with pandas, they write the for loop because they're trying to pass in those indices. And I don't blame them, because like if you've programmed before, that's how you would do it. But we have to know that we are now working with a data set. All of our data is already stored in columns, and we can utilize that structure already to make things faster and less complicated. So I will rerun that example on my computer, and I guess I have to fix the installation instructions. But I will put the Numba example in the notebook for you. And so the last bit of class I want to cover is sort of putting it all together. We'll begin with a few random things first. So I'm going to create a new Python notebook. First thing about this is sort of like useful Python information. The number 1000 in Python, numbers with the underscore in a number doesn't matter. So it's really helpful if you use a delimiter somewhere. You can put that underscore in a number to help you count. So like instead of counting 6 zeros, you can see this is a million because there's a delimiter there. If you're in India, I think they use the lakh in the 10,000ths position. You can use that there too. It doesn't matter. The underscore doesn't matter in numbers. Other thing, as a list, you can have an empty object at the end of the list, and it's going to be the same thing. So having that extra comma at the end of the list is okay. And the reason for that is if you have a situation where you're trying to have multiple things on in a list, you can end with a comma, and you don't have to do this weird thing where you comment out the last comma at the end when you're trying to add new things. So this is more useful if you're working on version control things. Sorry, you end up doing like, I want to comment out the 3, but you also have to comment out the trailing 2. You don't have to do this. you can leave that last trailing 2 and it's the same thing. And this helps a lot with version control. So you have fewer diffs in your actual source code. All right, so one other thing I want to show you guys before we move on. This is actually like data related now, is this notion of a dummy variable. So let me import Seaborn as SNS. So I'm using the Seaborn library. It's a plotting library. We don't really have time to cover plotting. So Seaborn load data set has a function called hold on, I realized like my chat didn't actually scroll. So one of the comments was like, is the process to create a function that operates on a univariate case and then vectorize it to the general case? Like, yes, that is what I highly recommend. And it's because in the simple univariate case, you can test it yourself. You are less reliant on like, oh, I have to set up this entire data set for me to test this function. No, that way you can test your function, input your own values, put the vectorize on top, and then pass in the whole column of values from your data set. It makes it much more easy. It makes it easier to write. It makes it easier to test and figure out like what's going on, because you might have a bad value in your data set. Then you can manually go back to the function, plug those in manually, and then see what's going on with that specific use case. So yes, my suggestion is always write the function as if it's not reliant on data, just individual isolated inputs, and then run np vectorize on it, because it's essentially a free operation, and then do it that way. All right, cool. So we have our tips data set. We have tips. So the first thing I want to show you is what is a dummy variable. In the dummy variable is something you'll hear from the statisticians. I don't know why they call it a dummy, but it's a dummy variable. From the engineering/computer science world, you might hear this called one-hot encoding. They mean exactly the same thing. And so what does this look like? So in Pandas, so we can import Pandas as PD. Pandas has a function called get_dummies. And we can give it our tips data set. And let me describe the before and after, right? So before we did it, we have total bill. So this is a data set that's saying like, what is the total, how much tip do you get given the total bill, given some other parameters of our table. Some of these columns are strings, and these strings represent different categories. So sex in this data set only has male and female. Smoker only has yes and no. Day is Thursday, Friday, Saturday, Sunday, and then time is lunch and dinner. And then we have another continuous variable for the table size. Once we run it through get dummies, you'll notice that, for example, right here, I'll use smoker. Smoker yes, smoker no. It essentially did that pivot for us, right? It took that column, pivoted for us, and then told us whether or not this person is a smoker or not a smoker. So if this person got a 0 for yes and a no for, and a 1 for no, this person is not a smoker, right? Same thing with days of the week. If it's 0 for Thursday, Friday, Saturday, and has a 1 for Sunday, then for that row, it was a Sunday. If I look at here, back to smoker, yes and no, because it's a simpler 2 example case. These 2 values are kind of redundant, right? If I have a 0 for smoker, yes, then I already know this person is not a smoker and the value is 1. Right? And vice versa. If I got a value of 1 for smoker, yes, then I can predict that it's going to be 0 for smoker no. There's no such thing as having a yes and no smoker. That doesn't exist, especially when we dummy encode. So in get dummies, there's a parameter called drop first, and whatever the first thing it encounters in your data set, it'll drop that. And so now we know that if the smoker no is a 1, then we know they are not a smoker. And if this value is 0, then we know that they are a smoker, right? And this becomes really important depending on what type of statistics you do. Like, let's say we're doing regular linear regression. If one column completely predicts another column, that becomes a problem in the actual math under that statistical method, right? So some stats methods require you to run drop first, others don't. Why do we want to run dummy variables when we are working with our data? And it's because if I were to go back to our original data, and if you roughly know how statistics works, the output, if we were to predict on tip, it doesn't make sense to say turning from what is it, like turning from male to female, like a single person in this particular data set does not turn from one sex to another, or it doesn't turn from one smoker to another, or it doesn't turn from Thursday to Friday, right? Like that observation is specifically for that one event. And so that's why we need to create like these dummy variables, and dummy variables only happen for categorical variables. So that's another pre-processing that you're going to have to do when you are working with data before you pass it into a statistical model. So I told you a lot about processing data and creating these dummy variables. Let's go and actually fit a linear regression model off of all of this. So we can say from sklearn import linear model. Dummy variables can be converted to tidy format. The answer is yes. You could repivot this down if you want. Typically, the dummy variable step is what you do after you process your data, because over here, you want your data in tidy format, and then you turn it into dummy variables. So dummy variables, that step is what you do right before you fit a model. This is a step that is model specific. It's very unlikely you need to do dummy variable stuff for your own like data processing, like regular data cleaning. It's unlikely you need that. And so this dummy variable step is what you do when you are going to fit a model. So we're going to fit a linear model. How does this work? We say linear model is equal to this linear model function. There's different types of linear models in scikit-learn. The one that we are going to be using is regular, like draw a straight line. So linear regression is the model that we're calling for linear model. Scikit-learn, this syntax looks really weird and awkward. But the thing is, once I show you how this works once, all of the scikit-learn models follow the same exact pattern. There is a way to drop something other than the first value. You can manually sort, like use an arrange function to sort it the way you want. I'm trying to think. There is a way where you can specify, like, for this column, drop this thing and that thing. So there is a way to do it instead of just like treat the first one. For time's sake, I'm just saying, like, let's just do it for the first one so I can get through the example. But yeah, there's a way to be a little bit more fine-tuned. So in scikit-learn, the first thing that we do is we create the model object. So this is the actual model that we are using. It is a linear regression model that we find in the linear models, one of the linear model features in scikit-learn. Right? So they have a whole bunch of models in there. We're using specifically linear regression. The next thing that we do is we take our linear model and then we call fit, like literally like put in values for a linear model. You're going to pass in two things, an X and a Y. So the X are your X's, your predictors, your independent variables. It is a capital X because it's most likely a matrix. So it's got multiple columns. So here, X, we are going to say tips. And what are our columns that we want? We want to we want to use total bill and size, right? So this part is very similar from the first hour, where we're subsetting parts of our data set, total bill and size, and then our Y, our response variable, our dependent variable, those are all synonymous, is going to be tips, and then the tip column. And key error usually means I spelled something wrong. Total bill size. Did I spell something wrong? I did spell something wrong. Oh, I know what I did. So remember, if I'm passing in multiple things, I need 2 square brackets. There we go. So that's how we actually go and fit the linear regression. It is a lowercase y, and this, like, if you ask the person who wrote this, they profusely apologize for this notation. It is lowercase y because typically your response variable is a single column or one vector, not a matrix. And so this comes from the math notation where matrices are always capital lettered and vectors are lowercase lettered. And so that's why it's capital X, lowercase y. If you tell yourself that story multiple times, it'll make sense. It does, but yeah, it makes people really angry. But if you come from the math world, or the stats world, really, that's how stats and math. If you come from that world, it makes sense in that sense, but it makes people who program really annoyed because, like, you have this random capital letter in here. And so, yeah, I have no idea how to, I am angry as well, is all I can say. Okay, so that's it. Once we run fit, we have our model. We fit our model. Like, fitting models, literally the easiest part in the world. We can predict or get a sense of what is the tip given total bill and size of the table. How do we get those values? We say lr.coef underscore, and that is the coefficients. And then we can say lr.intercept, lr linear regression.intercept, and that is the intercept of our model. So if we look at the actual formula, it'll be the predicted tip is equal to 0.67, that's the intercept, plus the value of total bill times 0.09 plus the value of size times 0.19, right? So a new table comes in, I can get a prediction of their tip by saying, what is their total bill? How many people in their party? And then solve for this right side part of the formula, and that'll be my predicted tip. So how does this work when we are working with dummy variables? So I'm going to copy and paste this little bit again. So we can write tips dummy, tips, sorry, code was wrong. All right, so we have our dummy version of our tip. How do we then use the same thing? Let's put in all of our variables in here for tip. I'm trying to make this a little bit simpler. Okay, tips dummy is equal to that. And then maybe I only care about, for this example, the tip column, the total bill column, and then sex underscore, actually let's use smoker underscore no, right? So we have a smaller version of our tips data set. And then we can do the same thing just like before. If we're trying to fit this model, we can scroll up to the top. All we're doing is creating a linear regression object. So LR, we can call this LR2 if we want. And then all we do is LR2.fit. What are your X's? So X is going to be tips dummy. So one simple way we can use that .loc ILOC notation, all the rows, and then the second column all the way to the end. And then for our Y, we can have tips dummy the tips column or tip column. Right, so remember ILOC was something we talked about at the very first hour. What this is doing is saying, give me all of the rows from the index position of 1, which is the second column, give me all of the columns in my data set, except for the first one, because the first one is the one we're going to use for our Y. So all of that stuff's about like how to select different columns and stuff become really important when you start like saying like, I want to fit a variable, I want to fit a model on all of these columns. Here are all of my X's, and this is my Y. So we have our linear regression model, and then just like before, we can look up our coefficients and LR2.intercept, and that would give us the parameters for the formula that we would need, which would be tip is going to equal the intercept, which is 0.81, plus our value for total bill and whether or not they're a smoker. So this is going to be total bill times whatever this number is, plus their smoking status times that. So if they're not a smoker, this part will equal 0, and then we only care about their total bill. Right, so how do we interpret all of these numbers? So this total bill number, because that's the first variable we passed in, it means that for every 1 unit increase in total bill, so in regular English is for every dollar the total bill increases by, we can expect that the tip will increase by 10 or 11 cents. For this, it means that what does it mean for 1 unit increase for smoker? Well, it means from smoker going from 0 to 1, right? So smokers, if you are a smoker compared to a non-smoker, you are expected, or this data set shows that the tip will increase by about 15 cents for each dollar, or for each smoker compared to a non-smoker. So that's how you interpret those values. The other way that you'll see when you're working with, so that's how you interpret the individual values. In scikit-learn, it's so optimized for doing large prediction problems. I have to like mock up this data set a little bit. So we have our tips data set. Hold on. Give me 1 second. I have to mock up this data set, but this is something you wouldn't really do. So let's say I have give me 1 second. I have to fake an example. All right, so here's let's say we have some new data, right? It's not really new data because I'm literally pulling from the same data set we fit our model on. So it's not exactly like new unforeseen data. But the whole reason why we're fitting these models is because we want to see like if a new data set comes, a new total bill and smoker status comes in, what is the actual tip? And so we have this LR2 model. There's literally a function called predict. And from predict, we can literally give in, I believe we can just pass in new data, and it'll give us for each value of new data what it is. So let's put this into a new column, predicted tip, predicted tips is equal to that. So remember, how do you create a new column of data pretending it already exists? Because we know that the two sizes are the same, it can do that for us. And so now, given our new data set, which doesn't contain the tip column, which makes sense, usually new data doesn't have the thing that you're measuring. If you pass it into your model using .predict, you got the predicted values, right? So you don't have to put in individual values. I showed you the .intercept and .coef because that's for most statisticians and that's how you interpret the actual numbers. But scikit-learn isn't really made for all of that stuff, so it's a little bit hidden away. You have to use other functions to get the full statistical diagnostics. But for the most part, fit the model, predict on new data, and that's how you get predicted values. And if you want, you can like go back and see like how off how off the actual like values are. I guess we can compare it. It seems pretty off because the first one is like $1 and we predicted like $4. So they're oh no, sorry, it's the tail. All right, does that make sense? Yeah, it looks pretty much right. So the actual tip was $5.92 and we predicted $4.03. The last one was $3. We predicted $2.94. So maybe our model could have been better if we put in like day of the week. That probably makes sense. Genders definitely. I know this data set a little bit. Like the gender will actually play a bigger role into in the actual tip. And so that's how you go fit a model. And it all comes back to, well, we started off with a tidy data set, right? Because each column we can pick them out. And once we have those columns set up, we can turn them into dummy variables, and then we can go fit a model. So like all of those things relate to that second block of time where we talked about tidy data, because that is essentially like, I think is like the most fundamental and important thing in like the whole data science world. Because once you get that, you can pretty much like learn how to do everything else. The function thing usually is more complicated, and so I walk through that. But it's another way of showing you that like when you are working with data, you still have to learn about functions like normal computer science education, but you don't need to learn about actual explicit for loops because your data probably is already should be in a format where you don't need to write loops. So with that, that's really everything I wanted to cover. I somehow managed to like be a little bit early on things. What I will give to everyone is all of the notebooks right after the class. And then I will go back and write a little comment about every single statement. So you have like a little bit more of a reference as you're going through the actual code. as I'm going through it. And then I know within the next, I don't know, amount of time, all of the recordings will be on YouTube for all the workshops. So you always have that as a reference. Sometimes they get really good and they put the timestamp, but if I see it, I'll probably comment the timestamp for the different sections. So it's a little bit easier to jump around between sections. So with that, I will, so that's the actual code. That's the actual like fitting of things. And where's my actual GitHub repo? This is the actual GitHub repo that I have pasted. So yeah, I'll stick around for the next couple of minutes. Don't use the actual Q&A tab because I realize that's like a terrible way of like getting my attention because I can't see it, but I will stick around for some questions during the actual workshop, but if you have other questions, there is the actual Slack channel for this tutorial, for this conference. So you can always, if you have any questions about the stuff we covered here, feel free to ask me in there. I know like within a week or so after the conference, like the Slack channel essentially like no one responds to these things, including me. So if you have any questions during up until like roughly Sunday, because that's when the sprints are over, ask questions there. And I'll sort of stick around for some of the questions. So the question, one of the questions was like, which rows did I specifically fit? I didn't do this the proper like data science way where like you should not predict on your own data set. That's not how you do it. But I took the tail, which was the last 5 rows, just to mock up a data set example to do this in. I think that's something I need to keep in mind the next time I teach this, is to have an actual data set of new data or split it in the very beginning. So that's what I ended up doing. Again, that is only for this class as a teaching example, not what you will do in real life. What I didn't cover was a lot of the actual machine learning pipelining stuff, right? So how do we go and see that this is a good model? That is an entire workshop on its own. And then that's where you talk about like cross-validating and finding test data sets and predicting data sets and all of that. We didn't cover any of that, but I wanted to use this as a segue into how do we go from all of this data processing into like something else, not pandas. So one of the questions was, is it more efficient to use apply for gathering data for data visualization other than loops? I don't know if you can. I'm trying to think if you can. I've never used apply for putting together multiple data visualizations. What I usually do if you're using apply, and this is sort of why I use the Seaborn library a lot in Python, and it's because in Seaborn, it allows you to do what's known as a faceted grid. And so I think they actually use a tips data set. So let's say I have a scatter plot of total bill and tip, and I want a separate plot for sex and time of day, like a categorical variable. So that's when I would use Seaborn to split out my plot that way. As far as plotting goes, if you're using matplotlib, yes, I've totally seen for loops to write matplotlib code. So that is a thing. Most of the time, if I'm trying to make something like a figure for like a paper or something, I end up plotting in R. So I will like save out my data set either to a database or to a flat file and then load everything into R and make my final plots there. That's sort of just, I know how to control the plots better in R. But that's it. For Seaborn, there shouldn't be other libraries to import it. I guess the main thing is if you're using like a weird Python distribution with environments, make sure that Seaborn got installed in the right place. That's sort of like the main thing to watch out for. But Seaborn should be pip install Seaborn and it should just work. But if you have a question with that specific thing, I can help you walk through it in the actual Slack channel. Scroll back up to lr.fit. Okay. Yes. All right. So. But yeah, to Mike, I guess we can at least close the recording, and then I don't know if I still see other people's chat, but if it stops like chat from working and me talking to them, we can leave the recording on. To the person who is editing this video for YouTube, you probably cut it right now, or somewhere like before. Give me 1 second. So for Seaborn, what I would try is close Jupyter Lab, and then when you get that terminal back, run pip install Seaborn there, and then run Jupyter Lab again, and see if that works. So if you are using a subset of the rows, so instead of tips, all of tips, you would have to go back to like the first hour where you are doing all of the row subsetting first. So maybe you only want like .ilog 0 to 100, for example, for the first 100 that you want to fit on, or maybe you want to sample on 50. You can do that, and that's how you would do it. So you would do all of that processing before it comes into scikit-learn. So that's how you would subset on other combinations of rows. If no number shows up on the cell, that means your kernel is not, essentially your Python isn't on. So if you end up like typing something and every time you run it, it gets like, well, that wasn't helpful. No number shows up, or a star. The star means something is thinking, and then no number means that the Python thing is turned off, and you can hover your cursor on this little circle, and it should give you a sense of what Python is doing or the kernel is doing. What you can do is you can restart or interrupt the kernel, which essentially means like stop what you're doing. And then you can rerun your code again. So once you stop it, it's going to start over from the beginning as if you turned it off and turned it back on again. So that might also help with some issues. And you can rerun your code, and you'll see that when I rerun it, the numbering resets, and that's because it's essentially a brand new execution order. Why would LR not be running? That would, I would say, hopefully you first created the linear regression model and then you passed in the proper columns. Yeah, so if you want to have a different data for the fitting, you would create a separate data frame, fit on that, and then work on, and then do whatever you need. Having said that, that's probably what I should have done if I thought about a little bit ahead. I sort of like winged the last little bit of the tutorial. But yeah, what I should have done was subset the tips data set. So we have training data to fit the model, and then testing data to actually like see if our model went well. So that's what I should have done. But yeah, that's how you would do it in real life. And then scikit-learn itself has a lot of functions to help you do that. There's literally a function in scikit-learn called train test split. You give it a data set and it'll do all the splitting for you. So you have individual data frames to work with right away. That was more, that goes into more scikit-learn stuff. That's sort of, I didn't want to touch upon that. Sure, let me paste in all of this into one thing. So that is the lr.fit command that I ran. Make sure that like you have these things like worked, the tips data set loaded up, and then I think if you just run those 5 lines, it should work. But yeah, so there's like literally 1 more minute left. And so the notebook, if you give me about like 5 minutes after this recording ends, that will all be up there because I sort of didn't rename any of my notebooks. So that'll be there very soon. And then I will post into the Slack channel when I'm done updating with all of the comments for all of the code, because all of this stuff has no comments on it. So I'll have that later on, but I will push the notebooks in about like 2 minutes. So with that, I think, Mike, we can end this recording, and then I'll work on everything I owe all of the attendees.